Let's take a deep breath, relax, and slowly explore the story of water. Every drop of water you have ever drunk is older than the earth itself. The water in your glass this morning, the water in the rain that fell on your roof last night, the water in the rivers and the oceans and the clouds, all of it was made long before our planet existed. It was made in the darkness between the stars billions of years ago, when the simplest atom in the universe, hydrogen, met an atom of oxygen that had been forged in the heart of a dying star. Those two atoms bonded together quietly and without ceremony, and something was born that would, in time, make everything else possible. That molecule was water, and there is nothing else quite like it in all of creation. The story of water begins not here on Earth, but out there in the cold, dark clouds that drift between the stars of our galaxy. These clouds are called molecular clouds, and they are the places where new stars are born. They are vast and they are very, very cold, just a few degrees above the coldest temperature that is possible anywhere in the universe. And on the surfaces of tiny grains of dust within these clouds, water molecules form. They form slowly, one at a time, atom finding atom in the dark. But there are so many dust grains and so much time that the amount of water out there in space is almost beyond imagining. There is enough water floating between the stars to fill the Earth's oceans many thousands of times over. Water, it turns out, is not rare at all. It is one of the most common molecules in the universe. It has been found in the atmospheres of distant planets, in the tails of comets, in the rings of Saturn, and in galaxies so far away that their light has been traveling toward us for billions of years. But how did water get here, to this particular rocky planet, orbiting this particular ordinary star? That question has kept scientists busy for decades, and the answer is still being worked out. For a long time, the most popular idea was rather simple. The Earth formed about 4.5 billion years ago from a spinning disk of gas and dust. In those early days, our planet was a terrible place, a ball of molten rock, glowing red, bombarded by debris left over from the birth of the solar system. The surface was far too hot for liquid water, so the water must have arrived later, delivered by comets, those wanderers with their beautiful tails of ice sweeping in from the cold outer edges of the solar system. It was a tidy story, but when spacecraft visited actual comets and measured their water, the chemistry did not quite match. Scientists use a kind of chemical fingerprint to trace where water comes from, comparing the weight of hydrogen atoms in different samples. And the fingerprint of comet water turned out to be different from the fingerprint of Earth's ocean water. Something else must have brought us most of our water. Attention turned to a type of ancient space rock called a carbonaceous chondrite. These old, unmelted chunks of rock from the belt between Mars and Jupiter contain a good deal of water locked inside their minerals. And when scientists studied one that fell in England in 2021, they found that its chemical fingerprint matched Earth's oceans almost perfectly. The pieces were starting to fit together, but the full picture may be more complicated still. Some of Earth's water may have been here from the very beginning, trapped inside the rocks that formed the planet and released through volcanic eruptions as the surface cooled. Other water arrived during a period of intense bombardment, roughly 4 billion years ago, when the inner solar system was pelted with asteroids and comets for hundreds of millions of years. Whatever the exact recipe, the result was extraordinary. As the Earth slowly cooled over unimaginable stretches of time, the water vapor in its thick, churning atmosphere began to condense. The first rains fell onto a surface still hot enough to turn them instantly back to steam. But the planet kept cooling. The rains kept falling. And eventually, the water stayed. It pooled in low places, filled the spaces between volcanic ridges, and slowly, over millions of years, gathered into the first oceans. Those early oceans were nothing like the ones we know today. They were probably greenish, stained with dissolved iron, and far more acidic. There was no oxygen in the air, no blue sky above them, no life within them. but they were there, liquid and vast, covering most of the planet. And within their warm, chemical-rich waters, something quiet and extraordinary was about to happen. Roughly 3.5 billion years ago, in those ancient seas, the first tiny living things appeared. We do not know exactly how it happened, and that remains one of the deepest mysteries in all of science. But we do know where it happened. Life began in water. For billions of years, every living thing on Earth was a creature of the water. And even now, every cell in every living being, from the smallest bacterium to the largest whale, operates in a watery environment. We are, in a very real sense, water that has learned to think about itself. The Earth holds about 1.5 billion cubic kilometers of water. That number has stayed roughly the same for billions of years. No new water is being made. Very little is being lost. The water you drink today has been recycled through the planet's systems countless times. Some of the molecules in your glass may have floated in ancient seas, fallen as rain on Roman roads, or passed through the body of a dinosaur. Every drop is ancient, and every drop is borrowed. Of all that water, about 97.5% is salt water in the oceans. Of the small amount that is fresh, most is locked away in glaciers and ice caps or hidden deep underground. The water that is easy to reach, the water in rivers and lakes and the air around us, makes up less than 1% of 1% of the total. It is this tiny, almost impossibly thin film of accessible fresh water upon which every human civilization has been built, every crop watered, every city founded, every empire sustained. And that is the substance we are about to follow through the full sweep of human history, from the first irrigation canals scratched into clay to the desalination plants humming on the shores of the sea, from sacred rivers worshipped as goddesses to poisoned wells that brought death to millions, from the aqueducts of ancient Rome to the aquifers of the American West running dry. It all began out there, in the dark, between the stars, when a hydrogen atom met an oxygen atom, and something quietly remarkable was born. About 2,500 years ago, in a busy trading port on the coast of what is now Turkey, a man named Thales looked at the world around him and asked a question that, as far as we know, nobody had ever asked before. Not who made the world, which was the business of gods and myths, but what the world was made of. And his answer was water. Everything, Thales believed, came from water. The seeds of all things have a moist nature, he said. Heat itself depends upon moisture. Therefore, water must be the first and most basic substance, the one from which all else springs. Thales was wrong, of course, in the details. Water is not the building block of everything, but his intuition was quietly remarkable. He had sensed something that modern science has spent more than 2,000 years confirming, that water is unlike any other substance. It behaves in ways that break the rules that govern ordinary matter. And without its strange, stubborn refusal to behave like anything else, life, as we know it, would be impossible. For centuries after Thales, water was considered one of the 4 basic elements, alongside earth, air, and fire. This idea held firm for nearly 2,000 years. Water was thought to be something that could not be broken down into anything simpler. It was just water. It was not until the late 1700s that this assumption was finally shattered, and the shattering came through one of the great priority disputes in the history of science. In 1781, a shy and reclusive English aristocrat named Henry Cavendish mixed 2 invisible gases together and set them alight. One was a gas he called inflammable air, which we now call hydrogen. The other was a component of ordinary air that we now call oxygen. When the 2 gases burned together, the result was startling. They produced pure water. 2 invisible things had combined to make a liquid. Water was not an element at all. It was a compound made of simpler parts. But Cavendish, who was famously reluctant to publish anything, did not rush to share his discovery. His assistant traveled to Paris and mentioned the results to a brilliant French chemist named Antoine Lavoisier. Lavoisier repeated the experiments, grasped their meaning immediately, and announced the findings to the French Scientific Academy as his own contribution. He gave the two gases their modern names: hydrogen, meaning water former, and oxygen, meaning acid producer. The question of who deserved the credit simmered among chemists for years. Cavendish, true to form, seemed not to care very much. What they had revealed was that every molecule of water is made of two hydrogen atoms bonded to a single oxygen atom. A structure so simple you could sketch it on a napkin. But this simplicity is deeply misleading. Water is, in the view of modern chemistry, one of the strangest substances known to science. It breaks expected patterns so often that entire textbooks have been written about all the rules it refuses to follow. The key to water's strangeness lies in the way its atoms share their tiny electrical charges. The oxygen atom pulls the shared charges toward itself, creating a slight imbalance. One side of the molecule carries a small negative charge, and the other side carries a small positive charge. This makes water molecules attract each other, the positive end of one drawn to the negative end of its neighbor. Each water molecule can form up to 4 of these connections at the same time, creating a constantly shifting web of linked molecules. This web explains almost everything unusual about water. It explains why water has such strong surface tension, strong enough to let small insects walk across a pond without breaking through. It explains why water can climb upward through the narrow tubes inside plant stems, defying gravity, pulling moisture from the roots all the way to the leaves. Without this property, trees could not exist. Plants could not grow. The land would be bare. The web of connections between water molecules also explains why water absorbs so much heat before its temperature rises. This is why the oceans act as the planet's great heat absorber, soaking up warmth from the sun during the day and releasing it slowly at night, keeping coastal climates mild and stable. It is why your body can cool itself by sweating. The water on your skin absorbs a great deal of heat as it evaporates, carrying that heat away from your body. Without this property, we would overheat far more easily. Water is also one of the best solvents on Earth. Because of the way its charges are arranged, water can pull apart the molecules of many other substances, surrounding them and holding them in solution. This is what makes blood possible, carrying nutrients and oxygen to every cell. It is what allows the chemistry of life to happen, all those countless reactions taking place in a watery environment inside every living thing. And it is also, less happily, what allows water to pick up and carry the germs and poisons that cause disease. But perhaps the most famous oddity of water is what happens when it freezes. Nearly every substance in nature gets denser when it becomes solid. Water does the opposite. As it cools toward freezing, it actually expands. The connections between its molecules lock into a pattern that takes up more space than the liquid form. Ice floats. This simple fact, which seems almost trivial, is one of the most important properties of any substance on Earth. If ice were heavier than water, lakes and oceans would freeze from the bottom up. Each winter, the ice would sink, and more water above it would freeze and sink in turn, until entire bodies of water were solid blocks of ice that would never fully melt. Life in the water would be impossible. Instead, because ice floats, it forms a blanket on the surface, insulating the liquid water beneath and protecting the creatures that live in it. Can you picture that for a moment? Imagine a world where ice did not float. Imagine the oceans freezing solid from the bottom, year after year, century after century. It would be a planet of ice, not a planet of life. There are other oddities too, worth pausing on. Water has a very high boiling point for a molecule of its size. If it followed the patterns of similar substances, it would boil at roughly 80 degrees below zero and the Earth's oceans would be gas. Water is also transparent to light, which is why sunlight can reach the plants and tiny organisms living in the upper layers of the ocean, feeding the base of nearly every food chain in the sea. Taken one at a time, each of these properties might seem like a small curiosity. Taken together, they amount to something like a quiet miracle. A substance that is liquid at the right temperatures for complex chemistry. A substance that floats when it should sink. A substance that dissolves almost everything, stores vast amounts of heat, and lets sunlight pass through it. Without any one of these properties, life on Earth would either look utterly different or would not exist at all. Thales of Miletus, standing on the shores of the sea 2,500 years ago, could not have known any of this. He knew nothing of molecular bonds or electrical charges, but he recognized something that all the science since has only confirmed. Water is not ordinary. It is the strangest, most unlikely, most essential substance in the known universe. And the story of humanity is, in every meaningful sense, the story of our long and complicated relationship with this molecule that refuses to behave like anything else. Sometime around 8,000 years ago, a farmer in southern Mesopotamia, in the flat, sun-baked land between the Tigris and Euphrates rivers, dug a small channel from the riverbank to a nearby field. It was not the first time anyone had done something like this. The act itself was simple, but what it represented was nothing less than the beginning of civilization. That little ditch, scraped into clay with a wooden tool, was the ancestor of every canal, every aqueduct, every reservoir, and every water treatment plant that would follow. It was the moment when humans stopped merely living beside water and began to control it. The connection between rivers and civilization is so deep that it is easy to take for granted. But consider the geography. The four oldest complex societies on Earth in Mesopotamia, along the Nile in Egypt, in the Indus Valley, and along the Yellow River in China, all arose along great river systems. This was not a coincidence. Rivers gave early farmers three things they needed to produce enough food to feed more than just their own families. Rivers gave them water for their crops. Rivers deposited rich soil during their annual floods. And rivers provided routes for carrying goods and people from one place to another. Without rivers, there were no food surpluses. Without surpluses, there were no cities. Without cities, there was no writing, no law, no organized religion, no standing armies. The river was the beginning of everything. In Mesopotamia, the land between the two rivers, the challenges were enormous. Unlike the Nile, whose floods came each summer with comforting regularity, the Tigris and Euphrates were wild and unpredictable. Their floods peaked in spring, just before harvest, when high water could destroy ripening crops. Water levels dropped during autumn, when farmers needed moisture most for planting. The rivers changed course without warning, sometimes abandoning entire communities that had built their lives along a particular channel. The response to this wildness was the earliest known large-scale irrigation system. By around 6,000 years before the Common Era, communities in southern Mesopotamia had begun building branching networks of canals supported by dikes and levees and small reservoirs. These were not simple ditches. They required careful planning, constant upkeep, and organized labor. Silt built up in the channels and had to be cleared out. Levees had to be rebuilt after floods. Disputes between upstream and downstream users had to be settled. And it was this need for coordination, many historians believe, that drove the creation of the first states. Irrigation at any real scale requires organization that goes beyond a single family or a single village. Someone has to decide when canals are opened and closed. Someone has to assign workers to dredge the channels. Someone has to settle arguments about who gets how much water. The earliest city-states of Sumer, and Uruk and Lagash were in many ways water management organizations as much as they were kingdoms. Their rulers kept records of canal maintenance. Their laws set out water rights, and their wars were often fought over access to irrigation channels. One of the oldest known border conflicts in all of history, between the cities of Lagash and Umma around 2,500 years before the Common Era, was at its heart a fight over canals. In Egypt, the relationship with water had a different character, but it was equally the foundation of everything. The Nile's annual flood, driven by monsoon rains thousands of miles to the south in the highlands of Ethiopia, was so regular that the Egyptians built their entire calendar around it. They divided their year into 3 seasons. The season of flooding, when the river rose and covered the land with a layer of rich, dark soil. The season of growth, when crops were planted in the freshly nourished fields. And the season of harvest, when the grain was gathered before the next flood arrived. The Egyptians measured the river's rise with devices built into its banks at key points, graduated stairways or columns that showed exactly how high the water was. The readings were matters of the greatest importance. Too little flooding meant poor harvests and hunger. Too much flooding meant destroyed villages and drowned animals. The ideal flood was one that rose just high enough to spread its dark, fertile soil across the widest possible area of farmland. Can you picture that? Imagine standing on the bank of the Nile in early summer, watching the water begin to rise, knowing that the next few weeks will determine whether your family eats well or goes hungry. The entire civilization of ancient Egypt, the pyramids, the temples, the great cities, all of it rested on this annual gift of water and mud. Far to the east, the Yellow River in China presented perhaps the most difficult water management challenge of all. The river carries enormous amounts of fine yellow silt, eroded from the dry plateaus of northwestern China. This silt gives the river its name and its color, but it also causes the riverbed to rise over time as the sediment piles up. Over the centuries, the Chinese built higher and higher walls of earth to contain the rising river, until in some places the Yellow River flowed 10 or even 20 meters above the surrounding plain, like a river balanced in the sky on earthen walls. When those walls broke, and they did break, the results were catastrophic. 3 floods in the years 1887, 1931, and 1938 collectively killed millions of people, making them among the deadliest disasters in all of human history. The Chinese response was to create one of the world's first societies organized around the management of water. The legendary figure Yu, celebrated in Chinese mythology for taming the Great Flood, is said to have spent 13 years dredging channels and diverting waters. From the very earliest dynasties through every one that followed, managing the Yellow River was considered the most important duty of the state, answerable directly to the emperor. 4 great river valleys. 4 great civilizations, each shaped in the most fundamental way by its relationship with water. The rivers gave humanity farming, surplus, cities, writing, and organized society. They also gave humanity floods, droughts, disease, and the first hard lessons about the limits of our control over the natural world. And every civilization since has been, in some way, a variation on this same ancient theme. In the early 1920s, an archaeologist working along the Indus River in what is now Pakistan began uncovering the remains of a city that had been buried for more than 4,000 years. What emerged from the dust was astonishing. Beneath the rubble lay a city of remarkable order, with broad streets laid out in precise grids, buildings made from standardized bricks, and, most remarkable of all, a water system that would not be matched anywhere in the world for the next 2,000 years. The city was called Mohenjo-Daro, and its relationship with water would change the way we think about the history of cities. The most famous structure at Mohenjo-Daro is a large rectangular pool, roughly 12 meters long, 7 meters wide, and about 2.5 meters deep. It was waterproofed with extraordinary care. its floor and walls sealed with a thick layer of a natural tar-like substance to prevent any leaking. Water was supplied by a well in an adjoining room, and a carefully built drain in one corner carried the used water away. This pool, known today as the Great Bath, sits on the highest part of the city in a position of obvious importance. Its careful construction and its prominent location suggest that it was not a swimming pool or a laundry. Most scholars believe it served some kind of spiritual or ceremonial purpose, perhaps connected to ideas about purity and cleansing that are still part of South Asian religious life today. If so, it represents one of the earliest known examples of the sacred use of water in human civilization, a connection between water and the soul that would echo through nearly every major religion in the ages to come. But the Great Bath, impressive as it is, was only the most visible part of a much larger picture. The entire city of Mohenjo-Daro was built around water. It had more than 700 wells, an extraordinary number, roughly one well for every 3 houses. No other ancient civilization comes close to that density. The wells were built with specially shaped bricks designed to hold the circular shaft under the pressure of the surrounding earth. Some wells were inside private homes. Others stood in public spaces, giving everyone in the city reliable access to fresh groundwater. The drainage system was equally remarkable. Every house in Mohenjo-Daro was connected to a citywide network of covered drains running along the main streets. Wastewater from bathing areas, kitchens, and toilets flowed through small channels in the house walls into these larger street drains. The main drains were lined with carefully laid bricks and covered with flat brick slabs to keep out dirt and smell. At regular intervals, there were inspection openings so the drains could be cleaned and maintained. Think about that for a moment. This was a city built more than 4,000 years ago in the Bronze Age, and it had covered sewers, indoor bathrooms, and a connected drainage network that ran through every neighborhood. Many houses had their own private bathing platforms, carefully paved floors with drains leading to the street system. Some houses appear to have had indoor toilets connected to the sewer network below. The presence of private bathing facilities in ordinary houses, not just in palaces or temples, suggests that personal cleanliness was something valued by everyone in this society, not just by the wealthy. The cities of the Indus Valley were laid out on careful grids, with streets crossing at right angles. The bricks themselves were made to a standard size, the same proportions used across the entire civilization, in cities separated by hundreds of kilometers. Whether this uniformity came from some central authority or from a deeply shared tradition, the result was the same. These were cities designed and built with a level of care and order that was exceptional for their time. What makes the Indus Valley water systems even more striking is how they compare with what other civilizations were doing at the same time. In Mesopotamia, around 2,500 years before the Common Era, cities like had limited drainage, with wastewater often running through open gutters or collecting in simple pits. In Egypt, even the grandest buildings relied on basic pit latrines. It would be roughly 2,000 years before the Romans developed a sewage system of comparable ambition. Why did the people of the Indus Valley invest so heavily in water? Part of the answer is surely practical. River floodplains are prone to waterborne diseases. Good drainage and clean water would have kept people healthier. Part of the answer may be cultural and spiritual. The emphasis on bathing and ritual purity suggested by the Great Bath hints at a worldview in which cleanliness carried deep meaning. And part of the answer is simply geography. A flat, flood-prone landscape needs active water management just to keep a city livable during the rainy season. At a smaller but equally important site called Lothal, in what is now the Indian state of Gujarat, archaeologists discovered what may be the world's oldest dockyard, a large rectangular basin connected to a river by a channel, designed to keep a steady water level for loading and unloading trading ships. The engineering at Lothal shows that the water skills of this civilization extended well beyond urban sanitation into commerce and trade. What makes the story of the Indus Valley water systems especially moving is the mystery of their end. Around 1900 years before the Common Era, the great cities were abandoned. Mohenjo-Daro, its sister city Harappa, and hundreds of smaller settlements were left to the dust and the weather. The reasons are still debated. Shifts in climate, rivers changing course, the drying up of entire river systems, all of these may have played a role. As the water that sustained the civilization moved or disappeared, the elaborate drains and wells became useless. The population scattered. The lesson is a sobering one. Even the most brilliant water engineering cannot protect a people if the water itself goes away. Mohenjo-Daro's drains and wells and its great bath are monuments both to human cleverness and to human vulnerability. And 4,000 years later, as rivers run dry and aquifers deplete across South Asia, the very same lesson is being learned all over again. On any given morning in the ancient city of Varanasi, India, thousands of people descend stone steps to the banks of the Ganges River. They come before dawn when the sky is still purple and the air carries the scent of sandalwood and marigold. They wade into water that is, by any scientific measure, severely polluted, and they immerse themselves completely, emerging with wet hair and peaceful faces, believing with absolute conviction that the water has washed away their sins. For devout Hindus, the Ganges is not merely a river. She is a goddess, Mother Ganges, who descended from heaven to earth, and her waters carry the power to purify the soul. This scene, repeated every morning for thousands of years, captures something very deep about the human relationship with water. Across nearly every culture and every era, in every inhabited corner of the world, people have given water a sacred meaning. They have worshipped it, prayed to it, feared it, and used it in their most important rituals. No other substance holds such a prominent place in the spiritual life of our species. And the reason is not hard to understand. Water gives life. Without it, everything dies. In a world where the reasons behind nature were unknown, where rain could mean the difference between survival and starvation, it was perhaps inevitable that water would come to be seen as something divine. In Hinduism, the connection between water and the sacred runs through every aspect of religious life. The Ganges is the most revered of India's holy rivers, but she is not alone. The Yamuna, the Narmada, the Godavari, and many others are all considered sacred. The great gathering known as the Kumbh Mela, which takes place every 12 years at a holy river confluence, draws the largest crowd of human beings anywhere on Earth. During the gathering in 2019, an estimated 240 million people attended over the course of the festival, all coming to bathe in the sacred waters. The act of bathing in a holy river is believed to cleanse not just the body, but the accumulated weight of past lives. In Christianity, water holds an equally central place, expressed through the ritual of baptism. This is the foundational ceremony, marking entry into the faith and symbolizing a kind of spiritual rebirth. The practice traces its origins to the baptism of Jesus in the Jordan River, as described in the Christian scriptures. The symbolism is rich and layered. Water washes away the old life. The descent into the water represents a kind of death, and the rising out of it represents new life. The Jordan River itself, where this founding event is said to have taken place, remains one of the holiest sites in the Christian world. Pilgrims have traveled to its banks for centuries, and many still wade into its waters to reenact the original baptism. Other sacred waters hold deep meaning in the Christian tradition as well. The spring at Lourdes in southern France, discovered in 1858 by a young girl named Bernadette, is believed by many to have healing powers. Millions of pilgrims visit Lourdes each year, and the Catholic Church has recognized dozens of healings attributed to its waters. In Islam, water holds a special place rooted in the teachings of the Quran. Water is described as the origin of all life and is central to the practice of purification. Before each of the 5 daily prayers, Muslims perform a ritual washing that involves cleaning the hands, face, arms, and feet in a specific order. This washing is not merely practical. It is a spiritual preparation, a cleansing of the outer body that mirrors the intended cleansing of the inner soul. When water is not available, a symbolic cleansing using clean earth may be performed instead, showing that the spiritual intention matters as much as the physical act. The well of Zamzam, located within the Grand Mosque in Mecca, is Islam's most sacred water source. According to tradition, the well appeared miraculously in the desert when the infant son of the Prophet Ibrahim kicked the sand while crying of thirst, and a spring burst forth from the ground. The well has been in continuous use for thousands of years. Pilgrims performing the Hajj drink from its waters, and many carry containers of Zamzam water home to share with their families. In Judaism, the ritual bath known as a mikveh serves as a means of spiritual purification. The mikveh must contain naturally gathered water, either from rain or from a spring or a natural body of water. Immersion in the mikveh marks important moments of transition, conversion to the faith, preparation for sacred days, and other occasions of spiritual significance. The rules governing the mikveh are detailed and precise, reflecting the deep importance of water in Jewish religious law. Buddhism, while less focused on water as a sacramental element, incorporates it in many ways. Water is one of the 4 elements in Buddhist thought. Monks use bowls of water as objects of meditation. In many Buddhist traditions, water is poured during ceremonies to dedicate spiritual merit to those who have passed away. In Japan, the practice of standing beneath a waterfall as a form of meditation and spiritual cleansing dates back centuries, connecting the physical experience of cold rushing water with the discipline of inner stillness. The spiritual meaning of water reaches far beyond the major organized religions. Indigenous traditions all over the world have their own profound relationships with water. For many Aboriginal Australian peoples, water sources are connected to the creation stories of the Dreamtime. Among the Maori of New Zealand, rivers and lakes are considered living ancestors, and in 2017, a river in New Zealand became the first in the world to be granted the legal rights of a person. In many African traditions, a water spirit, typically depicted as a beautiful woman associated with rivers and the sea, has been honored for centuries. Among the Lakota people of North America, the phrase that translates as "water is life" became a rallying cry during the Standing Rock protests of 2016, showing how ancient spiritual relationships with water continue to shape the struggles of the present day. In the Shinto tradition of Japan, visitors to a shrine perform a ritual hand-washing at a stone basin near the entrance before approaching the sacred space. The act is simple, but it is filled with meaning. The water cleanses the visitor, preparing them to enter the presence of the spirits that inhabit the natural world. Across all of these traditions, across every continent and every age, a common thread appears. Water is more than a physical substance. It is a bridge between the everyday world and something larger, something sacred. The act of washing, of pouring, of immersion carries a meaning that goes beyond the merely practical. It speaks to something deep in us, something that recognizes in water's power to cleanse, to renew, to give life, a force that touches the divine. Wherever humans have lived beside water, they have worshipped it. And that impulse shows no sign of fading, even now. In 1872, a young scholar working in the basement of the British Museum was carefully piecing together fragments of ancient clay tablets that had been dug from the ruins of a royal library in what is now northern Iraq. As he translated the wedge-shaped script, he realized with growing excitement that he was reading a flood story, one that bore unmistakable parallels to the biblical account of Noah. In the tale, a man is warned by a god that the gods have decided to destroy the world with a great flood. He is told to build a massive boat, to fill it with his family and the seeds of every living thing, and to seal it with pitch. The rains come, the waters rise. The boat floats for days across a drowned world. Eventually, the man sends out birds to look for dry land. A dove comes back, finding no place to rest. Then a swallow. Then a raven, which does not return, meaning the waters have gone down. The scholar, a man named George Smith, was reportedly so overcome by his discovery that he began to undress right there in the museum reading room. The text he had found was part of the Epic of Gilgamesh, dating to roughly 4,000 years ago, making it more than 1,000 years older than the earliest written version of the story of Noah. The existence of this older flood story with such precise parallels, the warning, the boat, the animals, the birds sent to find land, would reshape scholarship and raise a question that has intrigued people ever since. Why do flood stories appear in nearly every culture on Earth? The answer, at least in part, is straightforward. Floods are a universal human experience. Every culture that has ever lived near rivers, coastlines, or monsoon regions has experienced devastating floods. The Tigris and Euphrates, whose unpredictable waters inspired the Mesopotamian stories, regularly swallowed communities. There is geological evidence of truly enormous floods in prehistory, including one roughly 7,600 years ago, when the Mediterranean may have broken through a natural barrier and poured into the basin that is now the Black Sea, potentially drowning settlements and displacing thousands of people. Stories born from such events could have traveled far and wide across the ancient world. But the flood story is not just a Near Eastern tradition. In Hindu scripture, the god Vishnu takes the form of a fish to warn Manu, the first man, of a coming deluge. Manu builds a boat, ties it to the fish, and survives the flood that destroys all other life. In Greek mythology, the god Zeus sends a flood to punish humanity, and only 2 people survive by building a chest and floating on the waters for 9 days. They are told to throw stones over their shoulders, and the stones become new human beings. In Chinese tradition, the flood story takes a different shape entirely. The Great Flood is not a punishment from the gods, but a natural disaster, and the hero Yu tames it through 13 years of tireless labor, dredging channels and diverting waters. Unlike the passive survival stories of other cultures, the Chinese version celebrates human effort and engineering. Yu's success earns him the right to rule, and the founding of the First Dynasty, establishing a direct link between water management and political power that would run through all of Chinese history. In the Americas, flood stories are equally widespread. The Aztecs believed the present world was the 5th creation, and that one of the previous worlds had been destroyed by a great flood. In the Maya sacred text called the Popol Vuh, the gods destroy an early race of beings by water. Among the Inca, a god destroys a race of giants with a flood before creating humanity anew. Across North America, dozens of indigenous peoples have their own flood traditions, each one shaped by the landscape and the waters of their own homeland. Beyond the floods, water gods form one of the largest families of divine figures across global mythology. Poseidon, the Greek god of the sea, was among the most feared powers of the ancient Mediterranean. With his trident, he could command storms and earthquakes, and no sailor put to sea without offering him prayers. In the Aztec world, the rain god Tlaloc was worshipped with both reverence and dread at the great temple in the capital. His anger could bring drought, and his favor could bring life-giving rain. The Aztecs believed that a previous world had been destroyed by the goddess of rivers and lakes, placing water among the most powerful and dangerous forces in their cosmos. In Africa, a water spirit known as Mami Wata, typically depicted as a beautiful woman associated with serpents, has been honored for centuries across West, Central, and Southern Africa. She embodies the dual nature of water itself, beautiful and generous, but also dangerous and unpredictable. In Chinese tradition, the dragon kings of the four seas ruled the waters from crystal palaces beneath the ocean, controlling rain, floods, and tides. For roughly 2,000 years, Chinese communities prayed to the dragon kings for rain in times of drought and for mercy in times of flood. What is striking about water gods and water spirits across all cultures is their consistent ambivalence. Water deities are rarely purely kind. They are as likely to destroy as to create, as likely to drown as to nourish. And this reflects the lived experience of water itself. The same river that feeds the field can flood the village. The same rain that fills the well can wash away the road. The same ocean that carries the trading ship can swallow the fishing boat whole. Water is both the most essential and the most dangerous element in human experience, and the gods that people created to represent it reflect this duality with remarkable consistency. The flood myths and water gods of the ancient world are not relics of a distant, superstitious past. They are the earliest expressions of a relationship with water that still defines us. When a modern city builds a wall against a rising river, it is performing the same act as the ancient hero who sealed his boat with pitch. When a community prays for rain during a drought, it is reaching for the same hope that ancient peoples carried to the altars of their rain gods. The forms have changed, but the fundamental relationship has not. We are still, as we have always been, at the mercy of the water. Somewhere in the dry highlands of northeastern Iran, roughly 3,000 years ago, a group of workers began digging a shaft straight down into the earth. They were not looking for gold or gems. They were looking for water, and when they found it, seeping from an underground layer of water-bearing rock deep below the surface, they did something quietly brilliant. Instead of hauling the water up bucket by bucket, they dug a gently sloping tunnel from the water source all the way to the surface, stretching for kilometers across the desert floor. Vertical shafts were dug at regular intervals along the tunnel's length for air and for access, and the water flowed through the tunnel by the force of gravity alone, emerging at the far end as a steady, cool stream that could water fields, fill fountains, and sustain a city. No pumps, no fuel, no moving parts, just an understanding of how water moves underground and the patience to dig for it. This was the Qanat, one of the most elegant pieces of engineering in all of human history. The Qanat, known by different names in different places, originated in ancient Persia, most likely in the first 1,000 years before the Common Era. The technology may have first been developed to irrigate cotton fields, a crop that needed reliable water in a landscape where rain was scarce. Whatever its origin, the effect was immediate and dramatic. The Qanat made vast stretches of barren land productive, allowing farming and settlement in places that had been uninhabitable before. Building a Qanat required extraordinary skill. The workers who built and maintained them were specialists known as muqannis, and they were deeply respected. Their craft was passed from father to son across generations. The process began with finding a suitable source of underground water, typically at the base of a mountain range. The muqanni would dig a test shaft to check the depth and quality of the groundwater. If the water was good, the real work began. The tunnel, typically just tall enough for a man to work in, was dug from the lower end upward toward the water source, maintaining a very precise, very gentle slope, roughly 1 to 2 meters of drop for every kilometer of length. This slope had to be exact. Too steep, and the flowing water would erode the tunnel walls. Too shallow, and the water would not flow at all. The muqannis measured the slope using simple but clever tools, including oil lamps whose flames would flicker in the draft created by proper airflow, telling them if the tunnel was angled correctly. Vertical shafts were sunk every 20 to 50 meters along the tunnel. They served several purposes. They brought fresh air to the workers digging in the dark below. They allowed the dug-out soil to be hauled to the surface. And they provided permanent access points for cleaning and repairs. From above, a line of these shaft openings marching across the landscape looks like a trail of large anthills, and aerial photographs of the Iranian plateau show thousands of these distinctive patterns, the surface signature of a vast underground water network that once sustained millions of people. A finished Qanat could stretch extraordinary distances. Some in Iran run for more than 70 kilometers. The deepest shafts reach 300 meters below the surface. The water that emerges at the lower end is cool, clean, and flows continuously all year round without using any energy beyond gravity. The system is also remarkably well suited to dry climates because the water travels underground for most of its journey, losing almost nothing to evaporation, the great enemy of surface water in the desert. The impact on Persian civilization was profound. By turning barren land into productive farmland, Qanats supported larger populations, more food, and more prosperous cities. The wealth from Qanat-fed agriculture helped fund the expansion of the great Persian empires. The Persians understood the value of water, and they actively promoted Qanat building across their territory. The technology spread outward from Persia through conquest, trade, and cultural exchange. When the Persians conquered Egypt, they brought Qanat building with them. The technology traveled westward across North Africa, adopted by local communities in Morocco, Algeria, Tunisia, and Libya. When the Arabs crossed into Spain in the 8th century, they brought the technique along, and irrigation channels based on Qanat principles are still used in parts of Spain today. The Spanish later carried these methods to the Americas, where similar systems still function in the southwestern United States. The Islamic world embraced Qanat technology with particular enthusiasm. Islamic law established water as a public good, and the idea that no person could be denied drinking water aligned naturally with a technology that delivered water to entire communities rather than to individual owners. Charitable foundations called waqfs often funded the building and upkeep of Qanats, ensuring that even the poorest members of a community had access to water. The city of Yazd in central Iran sits at the edge of 2 deserts and receives barely 60 millimeters of rainfall a year. By any normal measure, a city should not exist there. But Yazd has been continuously inhabited for at least 3,000 years, sustained entirely by its network of Qanats. The system was recognized by UNESCO as a World Heritage Site in 2016. The social life surrounding Qanats was as impressive as the engineering. The annual cleaning and repair of a Qanat was a communal event, with villagers working together under the direction of the master Muqani. Water from the Qanat was divided among users according to a system of shares, often measured in units of time rather than volume, each family entitled to the full flow for a set number of hours. These arrangements were governed by local custom and enforced by community agreement, sometimes for centuries without interruption. Today, many of the world's Qanats are falling silent, victims of modern deep well pumps that drain the same underground water sources. A pump can pull water faster and cheaper than a gravity-fed tunnel, but it also lowers the water table in ways that Qanats, with their gentler approach, never did. In Iran, tens of thousands of Qanats have gone dry over the past century. The irony is a bitter one. A technology that sustained life in the desert for 3,000 years is being destroyed by a technology that may exhaust the same water supply in just a few decades. The Qanat stands as a reminder that the most lasting solutions to water scarcity are not always the most powerful or the most modern. They are the ones that work with nature rather than against it. And in a world facing growing water shortages, the ancient wisdom of the Muqanis may prove more relevant than ever. In 312 years before the Common Era, while Roman armies fought for control of southern Italy, a powerful official named Appius Claudius began 2 projects that would define his legacy. One was a great road stretching south from Rome. The other was a channel that brought fresh spring water from sources 8 miles east of the city through an underground tunnel into the heart of Rome. It was the city's first aqueduct, and it changed everything. For the first time, Rome did not have to depend on the muddy, increasingly dirty Tiber River or on scattered wells. It had clean, reliable water flowing by gravity from the hills into the city. And this was only the beginning. Over the next 5 centuries, Rome would build 11 major aqueducts, each more ambitious than the last. One ran 91 kilometers from springs in a distant valley. Another featured soaring arches that marched across the countryside on columns up to 27 meters high. Together, these 11 aqueducts formed a network that, at its peak, delivered between 500,000 and 1 million cubic meters of water every day to a city of roughly 1 million people. That per-person supply rivals, and in some cases exceeds, what many modern cities provide. The man who documented this extraordinary system most carefully was Sextus Julius Frontinus, appointed as Rome's water commissioner in 97 of the Common Era. Frontinus was a meticulous administrator. His detailed account of the aqueducts, describing each one's source, length, capacity, and condition, remains our best record of the system. He wrote with obvious pride, comparing the aqueducts favorably with what he considered the useless pyramids of Egypt. The engineering behind the aqueducts was remarkable. The fundamental principle was gravity. Water flowed from its source to the city along a channel that dropped very slightly, typically about 1 to 3 meters for every kilometer. Maintaining this gentle slope across rugged terrain required tunnels through hills, bridges across valleys, and sealed pipes that could carry water down into a valley and back up the other side. The famous arched bridges that we picture when we think of Roman aqueducts are among the most recognizable symbols of their engineering, but they actually made up only a small portion of the total system. Most of the channels ran underground or at ground level in covered trenches, protected from dirt and from people who might try to steal the water. Once the water reached Rome, it was distributed through a network of lead pipes to public fountains, bathhouses, and private homes that paid for the service. The word plumbing comes from the Latin word for lead, and the workers who installed and maintained the pipes were called plumbers. Frontinus records that the system included over 200 distribution tanks, and even the overflow from these tanks was put to use, flushing the city's sewers. The public baths were perhaps the most spectacular consumers of Rome's water. The great imperial bathhouses were among the largest buildings in the ancient world. One of them, completed around 216 of the Common Era, could hold an estimated 1,600 bathers at once and covered more than 25 acres. It had hot rooms, warm rooms, cold pools, exercise grounds, libraries, and gardens, all supplied by their own dedicated branch of the aqueduct system. Bathing was a daily ritual for Romans of every social class, and the baths served as gathering places where people met, did business, and discussed the affairs of the city. The Romans also built one of the ancient world's most impressive sewer systems. The main sewer, called the Cloaca Maxima, was originally constructed as an open channel to drain marshland. Over time, it was enclosed and expanded into a massive stone-lined tunnel that carried wastewater and rainwater to the Tiber. At its mouth, it was large enough to drive a cart through. Portions of it still function as part of Rome's drainage system today, more than 2,000 years after it was built. Can you imagine that? A sewer built in the age of kings, still doing its job in the age of computers. There are not many pieces of infrastructure that can make that claim. The question of whether Rome's lead pipes poisoned its citizens has intrigued people for generations. The Roman architect Vitruvius, writing during the reign of Augustus, explicitly warned against using lead pipes, noting that water carried through clay was healthier. Lead workers, he observed, often developed pale complexions and other ailments. Despite these warnings, Rome continued to use lead extensively. Modern studies suggest that heavy mineral deposits that formed inside the pipes may have created a barrier between the water and the lead, reducing the risk somewhat. But tests on sediment from the Tiber harbor show that lead levels during the Roman era were roughly 100 times higher than natural background levels, so the water did carry more lead than was safe, even if the full health effects remained debated. The fall of the Western Roman Empire in the 5th century brought the aqueduct system to a gradual end. Invading armies cut the channels to starve the city of water. Without the organized maintenance that the system demanded, the channels filled with silt, the arches crumbled, and Rome's population, which had once reached perhaps 1 million, shrank to perhaps 30,000. The great baths fell silent. The fountains stopped. The people of medieval Rome went back to drawing water from the river and from wells, as their ancestors had done before the aqueducts were ever built. It would be more than 1,000 years before any city in Europe again achieved a water supply to rival what Imperial Rome had enjoyed. The Renaissance popes eventually restored some of the old channels, and the famous fountains of Baroque Rome, the Trevi, the fountains of Piazza Navona, were fed by these revived waters, connecting the city's present to its ancient past. The Roman aqueducts were a statement of what centralized power, engineering skill, and enormous labor could accomplish when directed at the basic problem of bringing water to a thirsty city. But they were also, as the centuries that followed made clear, a fragile achievement utterly dependent on the political stability and economic strength needed to maintain them. When those vanished, the water vanished with them. And that is a lesson worth remembering. In the flat limestone plain of the Yucatan Peninsula, there are no rivers. There are no streams, no natural lakes, no ponds. The rain that falls on this porous land vanishes almost instantly, sinking through the rock into vast underground pools. For the Maya, who built one of the great civilizations of the ancient Americas here, water came from cenotes, natural sinkholes where the limestone ceiling had collapsed to reveal the water hidden below. These pools, some of them vast underground caverns with crystal clear water lit by shafts of sunlight through the broken roof, were not merely water sources. They were considered entrances to the underworld, places where the living world and the world of the dead touched each other. They held both practical and spiritual significance of the highest order. At the great Maya city of Chichen Itza, which flourished from roughly the 7th to the 13th century, one cenote was the focus of religious life. This vast circular sinkhole, about 60 meters across, with sheer walls dropping 27 meters to the water surface, was dedicated to the rain god, one of the most important figures in the Maya world. In times of drought, which were frequent and devastating, offerings were thrown into the cenote to ask the rain god for mercy. When the cenote was dredged in the early 20th century, the offerings recovered included gold, jade, pottery, and the remains of human beings, mostly children, whose tears were believed to encourage the god to send rain. The Maya developed clever water systems to supplement the cenotes. At the great city of Tikal, in the tropical lowlands of what is now Guatemala, engineers built a system of reservoirs, canals, and raised walkways that collected and stored rainwater during the wet season for use during the dry months. The largest reservoir at Tikal held an enormous volume of water. Sand filtration systems have been found at some of these reservoirs, showing that the Maya understood basic principles of water cleaning. Far to the north, in the Valley of Mexico, the Aztecs faced a different water problem and solved it with equal brilliance. Their capital, Tenochtitlan, was built on an island in a large shallow lake that was partly fresh and partly salty. The city's island location gave it natural protection from enemies, but it also created a serious problem. The lake water surrounding the city was too salty for drinking or growing crops. The Aztecs solved this with a series of remarkable projects. The most famous was the system of raised garden beds, sometimes called floating gardens, though they did not actually float. These were artificial islands constructed by weaving reeds around wooden stakes driven into the shallow lake bottom, then piling layers of mud, decaying plants, and soil on top until the surface rose above the water. The roots reached down into the lake, giving the plants a constant water supply. The system was extraordinarily productive, yielding multiple harvests each year of maize, beans, squash, tomatoes, and flowers. Fresh drinking water reached Tenochtitlan through a double-barreled aqueduct from springs on the mainland, roughly 5 kilometers away. The twin channels were a clever design, allowing one to be cleaned while the other kept flowing. And to protect the fresh water around the garden beds from the salty water in the eastern part of the lake, a massive dike was built, roughly 16 kilometers long, separating the two zones. It was one of the largest water engineering projects in the pre-Columbian Americas. When Spanish soldiers first saw Tenochtitlan in November of 1519, they were stunned. The city, home to perhaps 200,000 to 300,000 people, was larger than any city in Spain. Its broad causeways, its bustling markets, its temples and palaces rising from the lake, its network of canals serving as streets, all of it spoke of a civilization that had mastered water in ways the Europeans had never imagined. One of the soldiers later wrote that the site reminded them of enchanted things told of in legends. Within 2 years, the Spanish had destroyed the city, drained the lake, and begun building a new city on top of the ruins, a decision whose consequences, including chronic flooding and the slow sinking of the ground, plague Mexico City to this day. In South America, the Inca Empire developed water systems adapted to the extreme vertical landscape of the Andes Mountains. At a site called Tipon, not far from the city of Cusco, the Inca built a system of terraces, stone-lined channels, fountains and aqueducts that demonstrate a deep understanding of how water moves. Water from a high mountain spring flowed down through carved stone channels with carefully controlled slopes, spreading moisture evenly across terraced fields. Many scholars believe the site served both practical purposes for growing food and ceremonial purposes for honoring water. At another remarkable site called Moray, the Inca carved circular depressions into the earth, with concentric terraces that created different temperature zones from top to bottom. Each terrace level received its own water supply through separate channels, allowing the Inca to test different crops under different conditions. It may have been one of the earliest agricultural research stations in the world, and water management was at its heart. In the dry American Southwest, the ancestral Puebloan peoples developed water collection systems that sustained their communities for centuries in landscapes that receive less than 30 centimeters of rain a year. At Mesa Verde, in what is now Colorado, they built reservoirs and check dams designed to capture every possible drop of runoff. Water was treated as one of the most precious things in their world. And when a severe drought struck the region in the late 1200s, lasting roughly 25 years, the ancestral Puebloans abandoned Mesa Verde and migrated south. The cliff dwellings they left behind, with their empty reservoirs and dry dams, still stand as a reminder of how fragile civilizations can be when the water stops flowing. From the cenotes of the Maya to the lake gardens of the Aztecs, from the mountain terraces of the Inca to the desert reservoirs of the Southwest, the peoples of the ancient Americas developed water systems of extraordinary variety and skill. These achievements show the same truth that the river civilizations of the Old World had already demonstrated. Where water could be managed, civilizations grew. Where water failed, civilizations fell. Off the coast of what is now Israel, beneath 10 meters of Mediterranean water, lie the ruins of a village that drowned thousands of years ago when the sea level rose and swallowed the shore. The village is called Atlit Yam, and among its ruins, archaeologists found a well dating to roughly 6,500 years before the Common Era. It is one of the oldest known wells in the world. Its stone-lined shaft is still intact beneath the waves, a monument built by people who had only recently stopped wandering and settled down to farm. They understood something essential. If you want to stay in one place, you need to find a way to bring the water to you. Wells are among the most humble and overlooked pieces of human technology. They do not inspire epic poetry. They rarely make it into history books. But they are among the most important inventions our species has ever produced. A well allows a community to settle in a place where there is no river, no lake, no spring nearby. It frees people from the need to live right next to surface water, opening up vast stretches of previously uninhabitable land. The spread of farming across the dry landscapes of the ancient Near East, the establishment of trade routes across deserts, the building of fortresses in defensible but waterless positions, all of these depended on the ability to dig a hole in the ground and reach water. The earliest wells were simple shafts dug into earth or soft rock until they reached the water below. But as communities grew, wells became more sophisticated. The wells of the Indus Valley, as we explored earlier, were lined with precisely fitted bricks. Ancient Egyptian wells sometimes used wooden supports to prevent collapse. Roman wells were built from brick, stone, and concrete and were often fitted with mechanical lifting devices to draw the water up. If wells represent the simplest way to reach underground water, cisterns represent the simplest way to store water from the surface. A cistern is essentially a waterproof container, either natural or built, designed to collect and hold rainwater or water carried from somewhere else. The technology is ancient, and it is found in nearly every dry landscape where people have lived. In the desert of what is now southern Jordan, the people who built the remarkable city of Petra raised the art of water collection to extraordinary heights. Petra, carved from rose-colored sandstone cliffs, was one of the great trading cities of the ancient world, positioned at the crossroads of caravan routes linking Arabia, Egypt, and the lands around the Mediterranean. Its population reached perhaps 30,000 at its peak, in a place that received less than 150 millimeters of rain a year. That anyone could survive there at all was a testament to their skill with water. That a thriving city could flourish there was quietly remarkable. The builders of Petra constructed a water system that included dams, reservoirs, more than 200 cisterns, and a network of pipes stretching over 200 kilometers. They carved channels into cliff faces to direct rainwater into collection basins. They built dams across dry valleys to capture the brief but intense flash floods that occasionally roared through the desert. They lined underground cisterns with a waterproof coating to prevent any seepage. They designed their pipes with features that kept the water flowing smoothly and cleanly. The result was a desert city that not only had enough water to survive, but had enough for fountains, decorative pools, and even a public swimming area. The people of Petra showed that water scarcity is not just about how much rain falls. It is about what you do with the rain you get. Hundreds of miles to the northwest, the city of Constantinople, capital of the Eastern Roman Empire, developed what may be the most impressive cistern system of any city before the modern era. Constantinople sat on a peninsula with limited fresh water, and besieging armies regularly targeted its water supply. Having enough stored water was not just a convenience. It was a matter of military survival. The response was a massive program of cistern construction that continued for centuries. The most famous of these is a vast underground chamber built during the reign of the Emperor Justinian in the 6th century. This cistern covers nearly 10,000 square meters, its ceiling supported by 336 marble columns arranged in rows, many of them salvaged from the ruins of ancient temples. It held 80,000 cubic meters of water, supplied through channels from a forest 19 kilometers north of the city. Can you picture that space? Imagine walking through it, the cool, still air, the sound of water dripping from the vaulted ceiling, the columns stretching away in long rows into the dim light. It is like a cathedral built not for worship, but for water. But this great cistern was just the largest of a vast network. Over 200 cisterns from the ancient period have been documented in the city, including enormous open-air reservoirs covering areas larger than a football field. Together, they gave Constantinople enough stored water to survive prolonged sieges and droughts, and they were a key reason the city endured as a capital for more than 1,000 years. The technology of well digging advanced significantly over the centuries as well. In China, engineers developed a method of drilling by repeatedly dropping a heavy metal tool to chip through rock, which allowed them to sink wells to extraordinary depths. By around 1,000 years ago, Chinese engineers in the province of Sichuan were drilling wells over 100 meters deep to reach underground salt deposits, using bamboo tubes as casings and elaborate pulley systems to raise and lower the drilling tools. These techniques were centuries ahead of anything in Europe and would eventually influence the development of oil drilling in the 1800s. In medieval Europe, the village well was the center of daily life. It was where people gathered, where news was shared, where the rhythms of community life played out. In towns, public wells were maintained by local authorities and fiercely protected during sieges. The ability to deny an enemy access to water was one of the most effective weapons of medieval warfare, and many castles invested enormous resources in deep wells that could keep flowing even when surrounded on all sides. From the drowned well of Atlityam to the underground palace of Cisterns in Constantinople, the history of wells and cisterns is the history of our most basic relationship with water, the need to find it, to store it, and to make it available when and where we need it. It is a history without glamour, but without it, civilization as we know it would be impossible. Wells and cisterns are the quiet foundations upon which everything else was built. On the banks of the Orontes River in the Syrian city of Hama, a great wooden water wheel has been turning for centuries. It stands 21 meters tall, roughly the height of a 7-story building, and its rim is fitted with 120 collection boxes that scoop water from the river and lift it up to an aqueduct above. From there, the water flows to mosques, bathhouses, fountains, and gardens a kilometer away. The wheel turns continuously, powered by nothing more than the river's own current, lifting 200,000 liters of water every hour without consuming a single drop of fuel. The groaning of the Hama water wheels, a deep rhythmic creaking that fills the valley, has been described by travelers for at least 800 years. These water wheels are among the most vivid surviving symbols of a civilization that mastered water technology on a grand scale. The Islamic world that spread across the Middle East, North Africa, and Spain from the 7th century onward inherited the water engineering traditions of the ancient world, the Persian Qanat, the Roman aqueduct, the Byzantine cistern. But the Islamic civilizations did not merely preserve what came before. They refined it, extended it, and put it to use in the service of a vision of city life in which access to water was not a luxury but a right. Islamic law established water as a public good. The concept of the right of thirst guaranteed that no person or animal could be denied drinking water, regardless of who owned the land or the water source. Charitable foundations funded the building and upkeep of fountains, bathhouses, and water distribution systems throughout the Islamic world. The public drinking fountain, often built as an act of devotion, became one of the most recognizable features of Islamic cities, and many survive and still function today in Cairo, Istanbul, and Damascus. The technological achievements of this era were substantial. The most celebrated inventor in the field of water engineering was a brilliant craftsman from what is now southeastern Turkey, who in 1206 completed a masterwork describing dozens of water-powered machines. Among his creations were water clocks, fountains, and most importantly, a pump that used a mechanism to convert the spinning motion of a water wheel into the back and forth motion of pistons. This pump could raise water to great heights and deliver it under pressure, a principle that would not be widely adopted in Europe for centuries. His water clocks were marvels of precision and art. One device featured a model elephant whose rider struck a drum every half hour, triggered by a float sinking slowly in a bowl of water. When the bowl filled, a mechanism tipped it, emptied the water, and reset the clock. These devices were not merely decorative. They represented a deep understanding of how water could be used to power automated systems. In the gardens of Andalusia, in what is now southern Spain, water was transformed from an engineering necessity into an art form. The Alhambra in Granada, built in the 13th and 14th centuries, contains courtyards where fountains seem to defy gravity, sending water upward in gentle arcs without any visible machinery. The secret was elegant design, narrow pipes and carefully controlled water pressure, using the force of gravity from reservoirs on higher ground to push water through increasingly narrow channels until it rose as a graceful jet. The sound of flowing water, central to the Islamic garden tradition, was not an afterthought but a deliberate design choice, meant to create an atmosphere of coolness, peace, and spiritual reflection. The Islamic garden was conceived as an earthly image of paradise, with channels of water representing the rivers described in the Quran. This vision drove the development of garden design across the entire Islamic world. The Mughal gardens of India, including those at the Taj Mahal, inherited and expanded this tradition, creating spaces where architecture, landscape, and water merged into compositions of extraordinary beauty. The irrigation systems introduced by the Arabs to Spain during their 8 centuries of rule transformed the landscape of southern Europe. Elaborate canal networks turned dry land into some of the most productive farming regions on the continent. The Water Court of Valencia, which has met every Thursday at noon outside the cathedral door since at least the 10th century to settle disputes over irrigation water, is a living descendant of Islamic water governance. It was recognized by UNESCO as a part of humanity's cultural heritage in 2009. When the Spanish brought their farming traditions to the Americas in the 1500s, they carried with them techniques rooted in Islamic engineering. Irrigation channels in New Mexico that are still in use today trace their ancestry through Spain to the Arab engineers who first developed them in the deserts of the Middle East. The story of water, like the story of civilization itself, is a story of ideas flowing across borders and centuries, adapting to new landscapes while keeping the essential principles alive. The Islamic world also advanced the understanding of water itself. An Arab geographer writing in the early 1100s described the way water cycles through the natural world with remarkable accuracy, explaining how water rises from the sea, falls as rain on mountains, and seeps through rock to emerge as springs. His understanding of this process was 6 centuries ahead of European science. A contemporary mathematician described wells where water rises to the surface under its own pressure, a phenomenon that European scientists would not fully explain until the 1600s. In North Africa, the great cities of the region developed elaborate water networks serving populations of hundreds of thousands. The city of Fez in Morocco built a water system fed by its river and supplemented by over 200 fountains and numerous underground channels. The famous leather-working workshops that have operated continuously since the 1100s relied on a dedicated water supply designed to minimize contamination of the city's drinking water. The public bathhouse, adapted from older traditions, became one of the defining institutions of Islamic urban culture. Unlike the Roman baths, which emphasized exercise and social display, the Islamic bath focused on spiritual and bodily cleanliness, closely tied to the requirements of ritual purity. Every mosque complex typically included a bath, a fountain, and a drinking water supply, making water the very infrastructure of religious life. The water wheels of Hammah still turn. The fountains of the Alhambra still flow. The irrigation channels of Valencia and New Mexico still carry water to fields. These are not museum pieces. They are living technologies, connecting the medieval Islamic world to the present, reminding us that water management is not a problem to be solved once and then forgotten. It is a relationship renewed with each generation between human need and the substance that makes all life possible. In 256 years before the Common Era, in the western reaches of the Chinese heartland, a hydraulic engineer named Li Bing and his son faced a problem that had plagued the Chengdu Plain for centuries. The Min River, a powerful branch of the Yangtze, flooded disastrously during summer rains and provided too little water during the dry winter months. Previous attempts to control it with dams had failed. Li Bing proposed a radically different approach. Instead of fighting the river, he would work with it. The irrigation system that Li Bing designed and built remains in operation today, more than 2,200 years later, making it one of the oldest and most enduring pieces of infrastructure in all of human history. Its brilliance lies in three elegantly simple parts. A wedge-shaped barrier built in the middle of the river splits the flow into two channels, one for irrigation and one for carrying excess water downstream. A low overflow dam allows floodwaters to escape from the irrigation channel, preventing it from being overwhelmed. And a narrow passage cut through a mountain spur controls the volume of water entering the plain. The beauty of the design is that it has no moving parts, requires no fuel, and uses the river's own behavior to manage itself. During floods, the barrier automatically sends more water to the outer channel. During dry periods, more water flows into the irrigation channel. The system adjusts to conditions on its own without any human hand. The result was the transformation of the Chengdu Plain into the most productive farming region in China, a breadbasket that would fuel the rise of the state that eventually unified all of China. Li Bing is still honored in the region today. A temple dedicated to him stands near the river, and local tradition holds that his spirit continues to watch over the system he built. His creation was recognized as a World Heritage Site in the year 2000, a testament to an idea that is as sound now as it was when first carved from the rock. China's most ambitious water project, however, was not for irrigation, but for transportation. The Grand Canal, stretching roughly 1,800 kilometers from the south of the country to the north, is the longest built waterway in the world. It was constructed in stages over many centuries, but the version that linked north and south as a single system was largely the work of an emperor in the early 7th century. The human cost was staggering. Over 3 million workers were forced to labor on the canal, and an estimated 2.5 million died from overwork, disease, and exhaustion. The suffering caused by the project helped bring down the dynasty that built it, but the canal itself endured and became the economic spine of China for 1,000 years, carrying grain from the fertile south to feed the armies and cities of the north. Thousands of miles to the southeast, the Khmer Empire, centered on the city of Angkor, developed what may have been the most sophisticated water management system of the medieval world. At its height in the 1200s and 1300s, Angkor was one of the largest cities on Earth before the Age of Industry, covering roughly 1,000 square kilometers and supporting up to 1 million people. In a tropical climate that delivered intense flooding during the monsoon, followed by months of drought, maintaining a steady water supply for that many people required engineering on a vast scale. The answer was the Barai, a massive rectangular reservoir dug into the earth to store monsoon floodwaters for use during the dry months. The largest of these measured roughly 8 kilometers by over 2 kilometers and held about 48 million cubic meters of water. Smaller reservoirs and a sprawling network of canals, moats, and distribution channels connected the Barais to farmland and neighborhoods throughout the complex. The decline of Angkor in the 1400s and 1500s may itself be a water story. Research into ancient climate patterns suggests that shifts in the monsoon during that period disrupted the hydraulic system that sustained the city. Canals silted up. The intricate water network that had fed hundreds of thousands of people gradually failed. Angkor was not conquered by an enemy army. In a sense, it was simply left without enough water. In Sri Lanka, the ancient kingdoms built a tradition of their own, creating thousands of small irrigation reservoirs connected to larger ones in a cascading system that stored monsoon rains and surface runoff for use throughout the year. Some of these reservoirs, built over 2,000 years ago, are still in use today. The United Nations recognized the Sri Lankan cascade system as a globally important agricultural heritage in 2017. On the island of Bali, a system of cooperative water management called the Subak has functioned for at least 1,000 years. The Subak is not just an engineering system. It is a social and spiritual institution in which rice farmers share water from a common source according to rules managed through a network of water temples. These temples, dedicated to the goddess of the lake, coordinate planting and harvesting schedules across entire river systems to ensure that water is shared fairly and that pest outbreaks are minimized. The Balinese farmers see water as a gift from the gods, and the temples serve as go-betweens, connecting divine generosity with human need. The Subak was recognized as a World Heritage Site in 2012. In India, the tradition of the stepwell reached its artistic peak during the medieval period. The great stepwells of Western India were not merely practical structures for reaching underground water. They were underground temples, their walls covered with hundreds of beautifully carved figures depicting gods, goddesses, and scenes from daily life. One of the finest, built in the 11th century in the state of Gujarat, measures 65 meters long, 20 meters wide, and 28 meters deep. It was designed as an inverted temple, a place where the holiness of the water increased with each step of descent toward the source. It appears today on the Indian 100 rupee banknote. Across Asia, from the gravity-powered genius of Li Bing to the berets of Angkor, from the cascade reservoirs of Sri Lanka to the water temples of Bali, civilizations developed water systems of remarkable variety and wisdom. What unites them is not a shared technology, but a shared understanding that water is the foundation of everything, and that managing it well requires not just engineering skill, but social cooperation, cultural meaning, and a deep respect for the natural world. There is a story that gets told so often it has become accepted as fact. In the Middle Ages, the story goes, water in Europe was so dirty and dangerous that nobody drank it. Instead, people drank beer and wine from morning to night, spending their lives in a gentle haze because the alternative was death. It is a charming story, and it appears in countless popular histories and television programs. It is also, for the most part, wrong. The truth about medieval water is both more ordinary and more interesting than the myth suggests. Medieval Europeans did drink water. They drank it from wells, from springs, from rivers, and from collected rainwater. The evidence is extensive. Medical texts of the period discuss the qualities of different water sources and advise on which are healthiest. Town records document the construction and upkeep of water pipes, channels, and public fountains. Monastery records describe elaborate water supply systems for abbeys and convents. The reason water drinking rarely appears in surviving stories and journals is probably not that it was dangerous, but that it was unremarkable. Nobody writes down that they drank water today. For the same reason, nobody today writes down that they breathed air. That said, medieval people were not naive about the quality of their water. They understood perfectly well that some water was safer than others. Numerous sources warn against water from marshy areas, stagnant pools, and places downstream of where waste was dumped. Tradespeople whose work polluted water sources faced fines in many towns. The issue was not that people could not tell clean water from dirty water. The issue was that growing towns were producing more waste than their water systems could handle, and the boundary between clean water and dirty water was often poorly maintained. Beer and ale were indeed consumed in large quantities in medieval Northern Europe, but the reasons were partly nutritional. Medieval ale was a significant source of calories and vitamins in a diet that was often lacking in both. The amount of alcohol was low, perhaps 3%, nothing like modern beer. Workers might drink several pints a day, not to get drunk, but because it was an efficient way to consume energy. In Southern Europe, wine served a similar purpose. Neither beer nor wine replaced water. They added to it. The most important development in medieval European water supply was the building of piped systems to bring fresh water into growing cities. London's first major water project was approved in 1237 when the city purchased several freshwater springs to the west and built a lead pipeline over 4 kilometers long to carry the water into the heart of the city. The terminal fountain, a public structure where people came to fill their buckets, became a prominent city landmark. More systems were added over the following centuries, and maintaining the water supply was considered one of the most important duties of city government. Paris developed its own water systems during the same period. Public fountains fed by spring water served a growing population, though the supply was never enough for a city expanding as fast as Paris was. Venice faced a water challenge unlike any other city in Europe, and its solution was wonderfully clever. Built on islands in a shallow lagoon, Venice had no natural fresh water at all. The surrounding lagoon was salty, and the sea was saltier. So, beginning around the 9th century, the Venetians designed a system of underground cisterns to collect rainwater. Each square and courtyard in the city was built with a subtle slope that directed rainwater toward a central drain, which fed into a cistern lined with clay to keep out the salt water. A layer of sand filtered the water before it settled into the cistern below. By the height of the Venetian Republic, the city had nearly 6,000 of these underground cisterns. The system had real limitations. High tides could flood the cisterns with salt water, ruining months of stored rainwater. Long dry spells could empty them entirely. During emergencies, water had to be brought in by boat from the mainland, an expensive and sometimes risky business. It was not until 1884 that an aqueduct was finally built to bring mountain water to Venice, ending the city's 800-year dependence on its cisterns. The medieval period also saw the widespread use of water mills, which harnessed the energy of flowing water for grinding grain, processing cloth, sawing wood, and hammering metal. A Great English Survey from 1086 recorded over 5,600 watermills in England alone, roughly one for every 50 households. By the 1200s and 1300s, watermills were among the most valuable properties in Europe, and disputes over the water rights to power them were a constant source of legal argument. The great monasteries developed some of the most thoughtful water systems of the era. At one abbey in Burgundy, a network of channels diverted river water through the forge, the kitchen, the latrines, and the fish ponds before returning it to the river. The system showed a remarkably integrated approach to water use, in which a single stream served many purposes one after another. The water carrier was a familiar figure in medieval and early modern cities. These workers, usually from the poorest classes, hauled water in buckets or barrels from public fountains, conduits or rivers to households that could not reach the water themselves. In Paris, water carriers remained essential well into the 1700s, and their trade was regulated by rules that set prices, routes, and standards. The medieval relationship with water was practical, complex, and far removed from the simple story of filth and drunkenness. Medieval people needed water, sought water, fought over water, and invested real effort and money in getting it and moving it where it was needed. The systems they built, from London's pipes to Venice's cisterns to the watermills that powered an emerging economy, laid the groundwork for everything that would come after. The myth of the waterless Middle Ages may be entertaining, but the real story is far more interesting and far more relevant to the water challenges we face today. In the summer of 1858, London experienced a heatwave that turned the Thames River into something approaching a weapon. For decades, the city's growing population had been flushing its sewage directly into the river through an aging system of drains that had originally been designed to carry only rainwater. By mid-century, roughly 3 million Londoners were producing waste that flowed untreated into the same waterway from which many of them drew their drinking water. The warmer the weather, the worse the smell. But the summer of 1858 was something else entirely. Temperatures soared. The river level dropped. The exposed banks of sewage-soaked mud baked in the sun, and the smell became unbearable. The Great Stink, as it came to be known, showed no respect for social class. The Houses of Parliament, which sit directly on the Thames, were particularly affected. Members of Parliament tried to hold sessions with windows sealed and curtains soaked in chemicals, but the stench forced its way in regardless. Committees were abandoned mid-meeting. Lawmakers fled to the corridors. Newspapers reported that the river had become a horror, a threat, not just to comfort, but to life itself. The crisis was the result of decades of worsening conditions. London's population had roughly quadrupled in the first half of the century, overwhelming a medieval waste system never designed for such numbers. The spread of the flush toilet, of all things, had made matters worse. Before flush toilets came along, most households used cesspits, which were emptied by workers who came in the night, shoveled out the waste, and carried it away in carts. The flush toilet was cleaner for each household, but simply moved the problem to the river, speeding up the contamination of the Thames. By the 1850s, the river was essentially an open sewer. 4 years before the Great Stink, a physician named John Snow had already shown the connection between dirty water and disease. During a cholera outbreak in the Soho neighborhood of London in 1854, Snow carefully mapped the addresses of cholera victims and traced the source to a single water pump on Broad Street. He discovered that a cesspit next to the pump was leaking sewage into the well. When the pump handle was removed, the outbreak faded. Snow also noticed a telling detail. Workers at a nearby brewery, who drank only the beer they brewed and never touched the pump water, were entirely spared. Snow's work was brilliant. But his conclusion, that cholera was spread by contaminated water rather than by bad air, went against the prevailing medical thinking of the time. The widely accepted view held that diseases were caused by foul-smelling air, not by specific germs in water. Snow died in 1858 at the age of 45 without seeing his theory accepted. It was only later, as the science of germs was developed by researchers in France and Germany, that Snow's work was recognized as one of the foundations of modern public health. The Great Stink, however, accomplished what scientific argument alone could not. The sheer unpleasantness of the situation, concentrated in the very building where laws were made, drove political action at remarkable speed. A bill was introduced to fund a massive sewage project. It passed through Parliament in just 18 days, an almost unheard of pace for legislation of such scale and expense. The project was given to Joseph Bazalgette, the chief engineer of the city's works department. Bazalgette's plan was bold and elegant. He proposed to intercept the sewage flowing toward the Thames through a series of large tunnels running parallel to the river on both banks. These intercepting sewers, built at a slight downward angle toward the east, would carry the waste far downstream away from the city, where it would be released on the outgoing tide. The sewage would no longer poison the drinking water of central London. When asked why his sewers were so much larger than seemed necessary, Bazalgette is said to have replied that they would only get one chance to build the system and must plan for the future. That foresight proved wise. London's population would more than double again, and his oversized tunnels handled the growth. The construction was one of the largest civil engineering projects of its age. Over 80 miles of main sewers were built, along with 1,100 miles of street sewers. The project consumed over 300 million bricks. The embankments that line the Thames through central London today were built as part of the project, enclosing the main tunnels within their massive walls. At the far end, ornate pumping stations with elaborate ironwork and decorations still stand as monuments to an era when even sewage was treated with a certain style. The effects were dramatic and immediate. Cholera, which had killed tens of thousands of Londoners across 4 major epidemics, never returned to the city after the sewer system was complete. The river gradually recovered. The smell diminished. The city became measurably healthier. Bazalgette was knighted, and he has been called the man who saved more lives than any other single official of the Victorian age. His system, continually maintained and updated, remains the backbone of London's sewage network today. London's sewer system became a model for cities around the world. Paris built its own comprehensive network. Hamburg, Chicago, and dozens of other major cities followed, each one prompted by its own crises of contamination and disease. The principle established by Bazalgette that sewage and drinking water must be kept far apart became the foundation of modern public health. It was not a glamorous idea. It was simply the recognition that waste and drinking water must be separated, a principle that the builders of Mohenjo-Daro had understood 4,000 years earlier, but that industrial London had managed to forget. The Great Stink was, in the end, one of the most important events in the history of public health. Not because the smell itself caused disease, though many believed it did at the time, but because the urgency it created forced the building of systems that actually did prevent disease. It was a case of the right thing being done for the wrong reason, a reminder that in matters of water and health, what sometimes matters most is not being scientifically correct, but making the problem so impossible to ignore that someone is finally forced to fix it. In the spring of 1832, a ship arrived at the docks of Quebec City carrying more than cargo and passengers. It carried cholera. Within days, people in the crowded immigrant quarters began to suffer violent illness so severe that their bodies drained of fluid within hours. Their skin turned a ghastly blue-gray. Their eyes sank into hollowed sockets. Some who felt perfectly well at breakfast were dead by nightfall. The disease spread along the St. Lawrence River to Montreal, then south into the United States, reaching New York, Philadelphia, and New Orleans before the year was out. Terrified citizens watched as their neighbors were carried away by something nobody understood and nobody could stop. This was the second cholera pandemic, and it would not be the last. Cholera would circle the globe 7 times between 1817 and the present day, killing tens of millions of people and transforming humanity's understanding of disease, water, and public health in ways that no other illness has matched. More than any other single disease, cholera is the one that taught the modern world to take its water seriously. The ancestral home of cholera is the great river delta where the Ganges and Brahmaputra empty into the sea, across what is now Bangladesh and eastern India. The tiny organism that causes cholera thrives in the warm, brackish waters of this delta, living among the microscopic creatures that drift in the current. For centuries, possibly for much longer, cholera existed as a disease of this region, causing outbreaks among local populations but rarely spreading far beyond. What changed in the early 1800s was connection. The expansion of global trade, the movement of armies and pilgrims across enormous distances, and the crowding of city populations into places with no proper water supply or sanitation, all of these created the conditions for cholera to travel the world. The first pandemic began in 1817, when a severe outbreak in the Delta region spread along trade routes to Southeast Asia, the Middle East, and East Africa. The second pandemic, beginning around 1826, was the one that truly shook the Western world. Cholera reached Russia, then Poland and Germany, then Britain, then North America. The disease struck with terrible speed and visible horror. Unlike slow illnesses, cholera could kill in hours, and the manner of death, the catastrophic loss of fluid, the blue discoloration of the skin that earned the disease its nickname, the Blue Death, inspired a deep and primal fear. In Paris, the epidemic of 1832 killed over 18,000 people. Riots broke out as rumors spread that the authorities were poisoning wells or that doctors were killing patients to study their bodies. 6 more pandemics followed, each sweeping across continents. The third, from 1846 to 1860, was particularly devastating, killing over 1 million people in Russia alone. The sixth, from 1899 to 1923, was the last to hit Europe hard, largely because by then Western nations had invested in water treatment and sewage systems. The seventh pandemic, which began in Indonesia in 1961 and is technically still ongoing, continues to affect communities across Africa, South Asia, and the Caribbean. The scientific story of cholera is as dramatic as the disease itself. In 1854, the same year that John Snow mapped the Broad Street outbreak in London, an Italian doctor named Filippo Pacini examined the intestinal tissues of cholera victims in Florence and identified the tiny comma-shaped organism responsible for the disease. But in an era that still blamed disease on bad air, his work was almost entirely ignored. He died in poverty, his contribution unrecognized. Nearly 30 years later, a German scientist named Robert Koch traveled to Egypt and then to Calcutta to investigate a cholera epidemic. Working in the cramped conditions of a makeshift laboratory, Koch isolated and identified the organism, confirming the waterborne route of infection that Snow had proposed decades earlier. Koch's discovery, backed by the growing acceptance of germ theory, finally achieved what Pacini's had not: widespread recognition that cholera was carried by contaminated water. The impact on public health was enormous. Each pandemic served as a brutal lesson in what happens when water supply and sanitation fail. International conferences were convened specifically because of cholera, bringing together representatives from many countries to discuss disease prevention. These gatherings laid the groundwork for the international public health cooperation that would eventually become the World Health Organization. In city after city, cholera epidemics forced the construction of modern water and sewage systems. London built its great sewers. A devastating outbreak in the German city of Hamburg in 1892, which killed over 8,000 people, led to the construction of one of Europe's most advanced water treatment systems. In the United States, the epidemic of 1832 pushed New York to begin planning the aqueduct that would bring clean water from upstate sources to the growing city. Cholera also exposed a cruel inequality at the heart of waterborne disease. In virtually every outbreak, the poor suffered far more than the wealthy. They lived in the most crowded neighborhoods, drank the most contaminated water, and had the least access to medical care. A doctor investigating a related epidemic in the 1840s put the matter plainly. He said that epidemics were symptoms not of germs, but of social and political failure, and that the real prescription was not medicine but clean water, education, and justice. Today, cholera remains a disease of poverty and broken water systems. An estimated 3 to 5 million cases occur every year, with over 100,000 deaths. A catastrophic outbreak followed the earthquake in Haiti in 2010, killing over 10,000 people, traced to sewage contaminating a river. The civil war in Yemen produced what has been called the worst cholera outbreak in modern history. In each case, the mechanism was identical to what it had been in 1832, human waste finding its way into drinking water and vulnerable people paying the price. The 7th pandemic has now lasted over 6 decades. It persists not because the science is unclear. It persists because billions of people still lack access to safe water and proper sanitation. Cholera is, in the most literal sense, a disease of water, thriving wherever the boundary between waste and drinking water has been allowed to collapse. It is the oldest and most persistent reminder that clean water is not a convenience. It is the difference between life and death. In the summer of 1906, a wealthy New York banker rented a vacation home on Long Island for his family and their household staff. Within weeks, 6 of the 11 people in the house fell violently ill with typhoid fever. The owners of the property, terrified their home would become impossible to rent, hired an investigator to find the source. The man examined the water supply, the milk delivery, the plumbing, and the food preparation, and found nothing wrong with any of them. Then he turned his attention to the household cook, a woman named Mary Mallon. When the investigator traced Mallon's employment history, he discovered a pattern. At nearly every household where she had worked, typhoid had broken out. Over several years, at least 7 families who had employed her as a cook had experienced cases of the disease, more than 20 people made ill, and at least 1 dead. Mallon herself had never been sick. She was carrying the disease inside her body, shedding the germs through her hands into the food she prepared while showing no symptoms at all. She was one of the first known healthy carriers of typhoid, and her story would raise deep questions about where public safety ends and personal freedom begins. Mary Mallon, who the newspapers would call Typhoid Mary, was forcibly taken from her home by health authorities and placed in quarantine. She was released a few years later on the condition that she never cook professionally again. When she was caught cooking under a false name at a hospital where 25 people fell ill and 2 died, she was quarantined a second time. She spent the last 23 years of her life in isolation on an island in the East River, dying there in 1938. Typhoid, like cholera, is spread through contaminated water and food. The organism lives in the human gut and is shed in waste. When sewage gets into drinking water, or when an infected person handles food without careful washing, the cycle continues. Before modern water treatment, typhoid was one of the most common and feared diseases in the world, killing roughly 1 in 3 of those it struck. The disease was especially devastating in armies, where crowded camps and poor sanitation created ideal conditions. During the American Civil War, an estimated 80,000 Union soldiers died of typhoid, more than twice the number killed in several of the war's most famous battles combined. If typhoid and cholera are the most well-known waterborne diseases, they are far from the only ones. Dysentery, caused by various types of bacteria and other tiny organisms, has been a constant companion of human civilization, particularly in times of war and upheaval. The disease killed more soldiers than bullets in nearly every major conflict before the 20th century. Armies from ancient times through the Napoleonic Wars and beyond lost far more men to contaminated water than to the weapons of their enemies. There is another waterborne illness that is worth pausing on because it may be the most physically disturbing of all. It is caused by a parasitic worm that enters the body when a person drinks water containing tiny crustaceans that carry the worm's young. Over the course of about a year, the worm grows inside the body, sometimes reaching nearly 1 meter in length. It eventually migrates to the skin, where it creates a painful blister. When the sufferer puts the affected limb in water to soothe the burning, the worm emerges and releases its young into the water, completing the cycle. The traditional treatment, practiced for thousands of years, involves slowly winding the emerging worm around a small stick, turning it a few centimeters each day over several weeks to avoid breaking it. Some scholars believe that the ancient symbol of medicine, a serpent wound around a staff, may actually have originated as a picture of this very procedure. In 1986, when a major campaign to eliminate this disease began, an estimated 3.5 million cases occurred every year across 21 countries. The strategy for fighting it was remarkably simple. Teach communities to filter their drinking water through cloth to remove the tiny creatures that carry the worm and prevent infected people from entering water sources. No vaccine was used. No medicine was given. The entire intervention was about changing the relationship between people and their water. By 2023, the number of reported cases had fallen to just 13 in only 4 countries. This disease is on the verge of becoming only the second human disease ever eliminated from the planet, and the first to be eliminated without a vaccine. The connection between water and lead poisoning represents another chapter in this long and dark history. The Romans famously used lead pipes in their water systems, and the Latin word for lead is the origin of the English word plumbing. Whether Roman lead pipes contributed significantly to health problems in the population has been debated for centuries. The Roman architect Vitruvius warned against lead pipes, recommending clay alternatives instead. Modern analysis of Roman skeletons has found elevated lead levels, though the degree of harm remains disputed. What is not disputed is the modern toll. In 2014, the city of Flint, Michigan, switched its water supply to a different source as a cost-saving measure. Officials failed to treat the new water properly, and it corroded the city's old pipes, leaching lead into the drinking supply. For over a year, roughly 100,000 residents, many of them from low-income communities, were exposed to dangerously contaminated water. Children, who are particularly vulnerable to lead's effects on the brain, suffered elevated levels that studies suggest may have lasting consequences. The Flint water crisis was not a failure from some distant past. It happened in the 21st century in one of the wealthiest nations on Earth. It was caused not by ignorance, but by negligence, cost-cutting, and a political system that failed to protect its most vulnerable citizens. It showed that waterborne disease is not merely a historical curiosity or a problem limited to poor countries. It is a permanent risk wherever the systems that provide safe water are allowed to weaken, wherever cost is put before health, and wherever the people who drink the water have less power than the people who control it. From typhoid to parasitic worms, from dysentery to lead poisoning, waterborne diseases have killed more people throughout human history than all the wars and earthquakes combined. They are the diseases of neglect, flourishing wherever water systems fail and retreating wherever they are properly maintained. The lesson they teach is simple, and it has not changed in 5,000 years. The quality of a civilization can be measured more reliably than by any other yardstick by the quality of its water. On September 26, 1908, a physician named John Leal did something that could have been considered either visionary or reckless, depending on whom you asked. Without specific permission from the court that had ordered him to provide clean water to the city of Jersey City, New Jersey, Leal began adding a carefully measured dose of a chemical disinfectant to the city's water supply. He did this because a lawsuit between the city and its private water company had reached a standstill. The court demanded clean water, and the company's engineer had concluded that a proper filtration plant would take years to build and cost a fortune. Leal believed there was a faster way. He had spent years studying how certain chemicals could kill dangerous bacteria in water, and he was convinced that a controlled dose, carefully measured and continuously applied, could make the water safe without harming the people who drank it. The experiment amounted to the first continuous treatment of a public water supply in the United States, and if people fell ill, Leal would bear the blame. The results were extraordinary. Within weeks, the levels of harmful bacteria in the water plummeted. The rate of typhoid fever, which had been stubbornly high in Jersey City despite years of other efforts, dropped sharply. When the court examined the situation, it found that the treated water met every standard of purity available. News of the success spread rapidly. Within 6 years, over 20 million Americans were drinking treated water. By 1918, more than 1,000 cities across North America had adopted the practice. This quiet revolution in water treatment has been called the single most important public health advance of the 20th century. It is credited with saving more lives than antibiotics, vaccines, or any other medical intervention. A study from 2004 estimated that the introduction of clean water technologies, primarily filtration and this type of chemical treatment, was responsible for nearly half of the overall decline in death rates in cities during the early 20th century, and for nearly all of the decline in infant deaths and deaths from infectious disease. Before treated water became widespread, typhoid alone killed roughly 25,000 Americans every year. Within a decade of widespread adoption, that number fell by more than 90%. But this revolution did not come from nowhere. It was the final chapter of a century-long effort to make drinking water safe. The story begins with sand filtration. In 1804, a man in Scotland built the first water filtration plant, using beds of fine sand to clean river water. The principle was simple. As water passed slowly through the sand, a living layer of tiny organisms formed on the surface that trapped and broke down harmful bacteria. The technology worked remarkably well and spread across Europe over the following decades. The most dramatic proof of sand filtration came during a cholera epidemic in the German city of Hamburg in 1892. Hamburg drew its drinking water from a major river and did not filter it. The neighboring city of Altona drew its water from the same river, downstream of Hamburg's sewage outfalls, but passed it through sand filters. During the epidemic, Hamburg suffered over 16,000 cases and more than 8,000 deaths. Altona, drinking water that was dirtier at the point of collection, had almost no cases. The comparison was so stark that it became one of the most convincing proofs that cholera was carried by contaminated water. Chemical treatment added a killing step to the physical removal achieved by filtration. The combination of the two, cleaning the water physically and then killing any remaining germs chemically, became the worldwide standard for water treatment in the 20th century. But this approach did not win acceptance without resistance. Many people were instinctively troubled by the idea of adding a chemical to their drinking water, and the opposition foreshadowed later controversies. The most contentious of these was the addition of a cavity-preventing mineral to public water supplies. Beginning in 1945, when a city in Michigan became the first to add this mineral to its water, studies showed dramatic reductions in tooth decay. By the 1960s, most major American cities had adopted the practice. But fierce opposition arose. Critics argued that mass treatment through the water supply violated individual choice. The debate became tangled with Cold War-era fears, and a famous satirical film from 1964 portrayed the controversy with memorable absurdity. The debate continues in milder form to this day. Modern water treatment has evolved far beyond the methods of a century ago. Treatment with a highly reactive form of oxygen was first applied to drinking water in France in 1906, actually 2 years before the Jersey City experiment. Ultraviolet light, which damages the inner workings of germs and prevents them from reproducing, became practical for large-scale use in the second half of the 20th century. Advanced membrane technologies can now remove particles, bacteria, viruses, and even dissolved salts with increasing precision. Yet, for all this sophistication, the basic principle established by John Leal remains the backbone of global water safety. A disinfectant is added to the water, the dangerous organisms are killed, and the water is made safe to drink. The original method, in its various forms, still treats the drinking water of most of the world's city dwellers. It is cheap, it is effective, and it continues working as the water travels through distribution pipes, killing any germs that might enter through leaks or cracks along the way. The heroes of this revolution are not well known. John Leal is largely forgotten. The engineer who designed the treatment system is a footnote. The man who oversaw the daily operations is unknown to the general public. These were not glamorous figures. They were doctors, engineers, and public health officials who understood that the most effective way to save lives was not to cure disease but to prevent it, and that the most effective way to prevent disease was to ensure that every person had access to water that would not kill them. It was a quiet revolution, fought not with dramatic breakthroughs but with pipes, pumps, and carefully measured doses. By any reasonable measure, it was the most important revolution of the 20th century. And the next time you turn on a tap and drink the water that comes out without a moment's hesitation, you are living in the world that these forgotten heroes built. In the Black Desert of northeastern Jordan, roughly 100 kilometers east of the capital, lie the ruins of one of the earliest known settlements in the world, a place called Jawa. When archaeologists excavated the site in the 1970s, they found something remarkable. In one of the driest places on Earth, where rainfall rarely tops 100 millimeters a year, the people of Jawa had built a network of canals stretching up to 8 kilometers, directing seasonal floodwater into depressions where it was captured behind walls of stone. These stone walls were designed to hold back the weight of the water using nothing more than their own bulk. The Jawa Dam, dating to roughly 3,500 years before the Common Era, is the oldest known dam in the world. Its builders understood a principle that engineers would not formally describe for thousands of years, that a wall can hold back water simply by being heavy enough. And this principle would be reinvented and scaled up over 5,000 years, from the modest stone barriers of the Bronze Age to structures that would alter the landscape of entire continents. The ancient world built many dams, though most were small. The Egyptians built one roughly 50 kilometers south of Cairo around 2600 years before the Common Era. It was ambitious, roughly 15 meters high, but it failed within a few years, apparently overwhelmed by a flood. The failure may have discouraged Egyptian dam builders for generations. In Sri Lanka, thousands of earthen dams created the tank cascade irrigation system that still functions today. In Mesopotamia, lower barriers diverted river water into irrigation canals, though the silt-laden rivers required constant upkeep. The Romans built dams across their empire for water supply and irrigation. One dam in Spain, built in the 1st or 2nd century of the Common Era, still holds water today, making it one of the oldest working dams on the planet. Roman engineers developed both solid gravity dams and buttress dams supported by structures on the downstream side, and their practical understanding of water pressure, while never expressed in mathematical formulas, was good enough to produce structures that have endured for 2,000 years. The modern era of dam building began in the 1800s, driven by three needs that came together at the same moment in history: water for growing cities, irrigation for expanding farms, and a new demand that no ancient builder could have imagined: electricity. The discovery that falling water could spin turbines to generate electrical power transformed the dam from a storage device into a power plant, and the resulting rush to build dams reshaped the face of every continent. The Hoover Dam, built between 1931 and 1936 in a canyon on the Colorado River, became the defining symbol of this age. It was built during the depths of the Great Depression, and its workforce of 21,000 men labored in conditions of extraordinary difficulty. Summer temperatures in the canyon regularly exceeded 45 degrees. Workers operated hundreds of meters above the canyon floor. The official death toll was 96, though the real number was likely higher. When completed, the Hoover Dam was the tallest dam in the world. It created the largest artificial lake in the United States, and its generators produced enough electricity to power hundreds of thousands of homes. The dam, along with the irrigation network that depended on it, turned the desert landscapes of the American Southwest into habitable, fertile, and prosperous regions. The dam-building frenzy accelerated after the Second World War. The United States, the Soviet Union, India, China, and dozens of other nations built massive dams, seeing them as symbols of progress and national strength. India's first Prime Minister famously called dams the temples of modern India. By the late 20th century, there were roughly 58,000 large dams worldwide, holding back about 15% of all the water that flows through the world's rivers in a year. The largest and most debated of all was the dam built on the Yangtze River in China, whose construction stretched from the mid-1990s to 2012. It stands 181 meters high and stretches over 2,300 meters long, creating a reservoir more than 600 kilometers in length. Its power generating capacity is the largest in the world, producing roughly 20 times the electricity of the Hoover Dam. But the human and environmental costs were enormous. Over 1.3 million people were forced from their homes. Entire cities were submerged. Irreplaceable historical sites were lost. The habitat of endangered river creatures was destroyed, and at least one species, the river dolphin that once swam in those waters, is now believed to be gone forever. The environmental backlash against large dams grew in the late 20th century. In India, a movement led decades of protest against a dam that displaced hundreds of thousands of people from tribal and farming communities. In the United States, the environmental movement prompted a rethinking of dam policy. In 1999, a dam in Maine was deliberately torn down, marking the start of a movement that has since seen more than 1,700 dams removed across the country. The removal of 2 dams in Washington state allowed a river to flow freely for the first time in over a century. restoring habitat for salmon that had been blocked for generations. The story of dams is a story of ambition and consequence. Every large dam represents a bargain, water storage and electricity, in exchange for displaced communities, drowned landscapes and damaged ecosystems. Some of those bargains have been worth making, others have not. The Hoover Dam made modern Southern California possible, but other dams and irrigation diversions drained the rivers that fed the Aral Sea, turning one of the largest lakes in the world into a toxic desert. The era of large dam building is not over. A massive new dam on the Blue Nile in Ethiopia was officially opened in 2025, the largest in Africa. But the age of building dams without counting the full cost, without asking the people who will lose their homes or the scientists who understand the downstream consequences, is slowly, unevenly coming to an end. The question facing this century is not whether to build dams, but how to balance the genuine benefits of water storage and clean energy with the equally genuine costs of changing rivers that have flowed freely since long before humans existed. On the morning of October 14, 1842, the city of New York threw the most extravagant water party in history. Cannons fired at dawn. Church bells rang across the island of Manhattan. A 5-mile parade wound through the streets with brass bands, military companies and floats depicting the sea god and figures representing health and abundance. At City Hall Park, a fountain built specially for the occasion shot water 15 meters into the air while the crowd roared with joy. The occasion was the opening of the Great Aqueduct, a gravity-fed channel that brought fresh water from a river 41 miles to the north all the way to the heart of the city. For the first time in its history, New York had a reliable, clean, abundant water supply. The celebration was proportionate to the desperation that had come before. New York in the early 1830s was a city drowning in its own waste. Its wells were shallow and contaminated. Its population, swelling with immigrants, was packed into buildings with no sanitation. When cholera arrived for the first time in 1832, it found a city perfectly set up for disaster, and it killed over 3,500 people in a matter of months. A devastating fire in 1835 showed another consequence of not having enough water. Firefighters could not draw enough from wells and cisterns to fight the blaze, and nearly 700 buildings burned. The fire, the disease, and the filth finally convinced the city's leaders that a modern water system was not a luxury, but a matter of survival. The aqueduct was designed by one of the finest engineers of the century. The system included a dam on the Croton River, a closed channel of stone and brick following the contours of the land for over 40 miles, and large storage reservoirs in Manhattan. Construction took 5 years and employed thousands of workers, mostly Irish immigrants, who earned about $1 a day for grueling labor digging trenches, laying masonry, and tunneling through rock. The principle was the same one that had guided the Roman aqueduct builders nearly 2,000 years before. Go to the source, build big, and let gravity do the work. The original Croton Aqueduct was eventually replaced by a larger one in 1890, and then by the vast systems that today deliver roughly 1.1 billion gallons of water every day to about 9 million people. The water travels up to 125 miles from reservoir to tap, through tunnels blasted deep beneath rivers and city streets. New York's water is considered among the best in the world, one of the very few large city supplies pure enough that it does not require filtration. New York was not alone in reaching across great distances for water. Victorian England produced its own impressive aqueducts. Birmingham completed a system in 1894 that brought water 73 miles from reservoirs in Wales. Manchester's system, completed the same year, carried water 96 miles from the Lake District, sparking fierce opposition from people who objected to damming a natural lake to serve an industrial city. That controversy anticipated by more than a century the environmental battles that would surround every major water transfer project of the 20th century. But no city's water story is as dramatic or as morally complicated as that of Los Angeles. In 1900, Los Angeles was a small city of roughly 100,000 people in a dry basin with just enough local water for perhaps twice that number. The city's leaders, particularly its water chief William Mulholland, recognized that without a vastly larger water supply, Los Angeles could never become the great city they envisioned. Their eyes fell on the Owens Valley, a fertile farming region more than 200 miles to the north, watered by snowmelt from the mountains. The methods by which Los Angeles obtained the Owens Valley's water have become a byword for political deceit and environmental harm. A former mayor traveled to the valley under false pretenses, buying up land and water rights from farmers who did not know they were selling to agents of the city. The federal government withdrew its own plans for an irrigation project in the valley, effectively handing the water to Los Angeles. The city's voters approved the funds, and construction began with a workforce of thousands. The aqueduct was completed in 1913, using only gravity to carry water across more than 200 miles of desert. At the opening ceremony, as water cascaded down the final spillway, Mulholland stood before the crowd and delivered what became perhaps the most famous 4 words in the history of American water. He said, "There it is, take it." The farmers of the Owens Valley did not share the celebration. As Los Angeles continued to acquire water rights and pump groundwater from the valley, the farming economy collapsed. Owens Lake, once one of the largest bodies of water in California, dried up entirely, becoming a barren salt flat whose wind-blown dust would later be identified as one of the worst sources of air pollution in the country. Frustrated valley residents dynamited the aqueduct multiple times in the 1920s. The conflict inspired a famous film that became shorthand for civic corruption. Later systems extended this approach even further. The California Aqueduct, completed in the 1970s, moves water from Northern California to the south, a distance of over 700 kilometers. The Central Arizona project pumps Colorado River water uphill across more than 300 miles of desert. In Libya, a vast network of pipes more than 2,800 kilometers long carries ancient groundwater from beneath the Sahara to coastal cities. The age of the Great Aqueducts transformed the geography of where people could live, cities that had no natural right to exist in their dry surroundings. Los Angeles, Phoenix, Las Vegas grew into vast metropolitan areas because engineers found ways to bring water from far away. But the cost was not borne by the cities that received the water. It was borne by the valleys, rivers, and communities from which the water was taken. That is the fundamental bargain of modern water supply. Abundance for some, scarcity for others, connected by pipes that most people never see and distances most people never think about. On a morning in April of the year 2000 in the Bolivian city of Cochabamba, a 17-year-old boy named Victor Hugo Daza walked into a street protest and was shot in the face by a soldier. He died instantly. Daza was one of at least 7 people killed during what has become known as the Cochabamba Water War, a months-long uprising triggered by the selling off of the city's water supply to a private company. Under pressure from international lenders, the Bolivian government had given a 40-year contract to a group led by an American corporation. The contract covered not just the city's pipes and pumps, but also the right to charge for rainwater collected in private cisterns and community wells. Water prices doubled almost overnight. For a city where many families earned less than $2 a day, the increase was devastating. The protests began in January and grew through February and March. General strikes shut down the city. The government declared an emergency and sent in the military. Tear gas filled the streets. Hundreds were injured. International news coverage of the violence, and particularly of Daza's death, turned the Cochabamba water war into a global symbol of resistance against water privatization. On April 10th, the government reversed its decision and returned the water system to public control. The example set in Cochabamba would inspire similar movements from South Africa to Ireland. Fighting over water is nothing new. The earliest known record of a war fought over water dates to roughly 2,500 years before the Common Era, when two Mesopotamian city-states fought over the rights to irrigation canals fed by the Tigris. One king diverted water from his rival's canals, and the resulting conflict lasted over a century. Water was worth fighting over then for the same reason it is today. Whoever controls the water controls the food, and whoever controls the food controls the people. The modern geography of water conflict is shaped by a basic fact. Rivers do not care about political borders. The Nile flows through 11 countries. The Mekong flows through 6. The Jordan, the Indus, the Euphrates, and dozens of other major rivers are shared by nations whose needs often clash. International law offers limited tools for resolving these disputes, and the principle that a country can do what it likes with the water inside its borders conflicts directly with the principle that downstream nations deserve a fair share. The Nile may be the most politically sensitive river on earth. Egypt, with over 100 million people living in a country that is 95% desert, depends on the Nile for virtually all of its renewable fresh water. This dependence has made Egyptian leaders intensely wary of anything upstream that might reduce the river's flow. When Ethiopia announced plans to build an enormous dam on the Blue Nile, which provides roughly 85% of the Nile's total water, Egypt saw the project as a threat to its very survival. The dam in Ethiopia is a massive hydroelectric project, and when its reservoir is completely filled, it will hold 74 billion cubic meters of water. Ethiopia argues that the dam will provide desperately needed electricity to its population, many of whom have never had access to electric power, and that it will help regulate flooding downstream. Egypt fears that the filling and operation of the dam will reduce the Nile's flow during critical periods, threatening its agriculture and its people. Negotiations among Egypt, Sudan, and Ethiopia have been ongoing for over a decade without resolution. The dam began filling its reservoir in 2020 and was officially opened in 2025. The dispute remains one of the most dangerous potential flashpoints on the African continent. The Colorado River tells a different kind of water conflict story, one fought not between nations but between states within a single country. A legal agreement from 1922 divided the river's waters among 7 states, based on flow measurements taken during an unusually wet period. The actual long-term average has turned out to be significantly less, and a prolonged drought, the driest stretch in at least 1,200 years, has made the gap between promise and reality painfully clear. The consequences are visible from space. The Great Lake behind the Hoover Dam was 95% full in the year 2000. By the early 2020s, it had fallen below 30%, exposing a stark white ring of mineral deposits on the canyon walls that marks where the waterline used to be. In 2022, mandatory water cuts were declared for the first time in the river's legal history, and the Colorado River no longer reaches the sea. For most of the year, the riverbed at the border with Mexico is dry, every drop consumed by upstream cities, farms, and industries before the water can complete its natural journey. Water conflict takes many forms beyond direct confrontation. In South Africa during the apartheid era, water policy systematically denied clean water to black communities while ensuring abundant supply to white neighborhoods and farms. After apartheid ended, the new government wrote the right to water into its constitution, but turning that promise into reality has proven far more difficult than writing the words. In the Middle East, the War of 1967 had significant water dimensions. The territory gained by one side in that conflict included control over the headwaters of the Jordan River and the underground water sources beneath the occupied territory. Access to water in those territories has been severely restricted ever since, and the water issue remains one of the most bitterly contested elements of the wider conflict. A research organization in California maintains a database documenting over 1,200 instances of water-related violence throughout history, from ancient canal disputes to modern conflicts in Syria, Yemen, and the African Sahel. The database reveals a clear pattern. Water-related conflicts are becoming more frequent and more intense, driven by growing populations, shifting climates, and the widening gap between how much water people need and how much they have. There is a famous saying often attributed to Mark Twain that captures the essential truth about water in the American West. The saying goes, "Whiskey is for drinking and water is for fighting over." Twain almost certainly never said it, but the feeling behind it is accurate. Water has been fought over for as long as civilizations have existed. The intensity of those fights is growing. The question is whether they can be managed through cooperation and law rather than through force, a question that remains, in many of the world's driest regions, very much unanswered. On November 17, 1869, a fleet of ships led by the French imperial yacht sailed through a narrow channel cut across the land bridge connecting Africa to Asia, linking the Mediterranean Sea to the Red Sea for the first time in modern history. The Suez Canal was 164 kilometers long. Its construction had taken 10 years, cost an enormous sum, and consumed the lives of an estimated 20,000 Egyptian laborers, many of them peasant farmers forced to work under terrible conditions. The canal shortened the sea route from London to India by thousands of miles and transformed the politics of the entire Eastern Hemisphere. Within a few years, Britain would invade and occupy Egypt to control the canal, and British soldiers would remain on Egyptian soil for nearly a century. The canal was, in the most literal sense, a waterway built to serve an empire. The relationship between water and empire is one of the oldest patterns in human history. Empires have always needed water, and they have built extraordinary things to get it. But they have also used water as a tool of control, a way of reshaping land, populations, and economies to serve imperial interests. The story of colonial water engineering is at once a story of impressive achievement and deep exploitation. The British Empire's most extensive water project was the canal system of colonial India. Beginning in the early 1800s, British engineers designed and built a vast network of irrigation canals across the plains of northern India and beyond. One of the greatest, completed in 1854, stretched over 500 kilometers with thousands of kilometers of smaller distribution channels. Another engineer opened vast areas of southern India to irrigation through a series of dams and canals on major rivers. The canals were presented by the British as gifts of progress, proof of the empire's civilizing mission. The reality was more complicated. The canals were designed primarily to grow export crops, cotton and indigo and opium, that fed British industrial and commercial interests. They disrupted traditional water systems that Indian communities had maintained for centuries. In many areas, the canals caused the soil to become waterlogged and salty, degrading the very land they were supposed to improve. And the work was done using forced or poorly paid labor, with Indian workers earning a tiny fraction of what British engineers received. The colonial irrigation system also created new forms of political control. Water became a tool of reward and punishment. Communities that cooperated with the colonial government received water. Those that resisted could be denied it. The canal system required elaborate administration, extending the empire's reach into the most remote villages. Control of water meant control of farming, which meant control of food, which meant control of people. It was the logic of the ancient hydraulic states of Mesopotamia and Egypt applied with industrial-era efficiency. The French Empire followed a similar pattern in North Africa. In Algeria, which France invaded in 1830 and held until 1962, the colonial government built dams, reservoirs, and irrigation networks that served primarily the European settler population. The indigenous Algerian people, who had managed their water through traditional underground channels similar to the Persian Qanat, found themselves cut off from both their land and their water. In Egypt, the British built a dam across the Nile at the First Cataract, completed in 1902, to store floodwaters for controlled release during the growing season. The dam increased cotton production, Egypt's main export and the raw material for British textile mills. The profits flowed to British commercial interests and to the Egyptian landowners who cooperated with the colonial regime. Japan's colonial water projects in Taiwan and Korea followed the same basic pattern. After taking control of Taiwan in 1895, the Japanese built an extensive irrigation system that turned over 150,000 hectares of land to rice production, increasing rice exports to Japan. In Korea, colonized from 1910 to 1945, Japanese engineers built dams and irrigation systems that redirected Korean farming output toward Japanese markets. The infrastructure was impressive, but it served the colonizer, not the colonized. The Dutch colonial story adds yet another dimension. In what is now Indonesia, the colonial government required peasants to devote part of their land and labor to growing export crops, particularly sugar. The irrigation built to support sugarcane redirected water away from rice paddies, reducing food production and contributing to the famines that periodically devastated the local population. The legacy of colonial water engineering is deeply mixed. Many of the canals, dams, and irrigation systems built during the colonial era remain in use today and continue to provide water to millions. The Great Canal in northern India still irrigates land. The system in Taiwan still waters fields. But these systems also established patterns of water use, particularly large-scale irrigation for export farming, that have contributed to environmental damage, falling water tables, and social inequality in the decades since independence. Perhaps the most symbolic colonial water project is the Suez Canal itself. Built by forced Egyptian labor to serve European strategic interests, it physically divided two continents and created a new reality in which control of a water route meant control of global trade. When the Egyptian president nationalized the canal company in 1956, triggering a crisis and a joint invasion by Britain, France, and Israel, he was asserting not merely sovereignty over a commercial asset, but sovereignty over water, the most fundamental resource of empire. The failure of the invasion and the withdrawal of European forces marked, in the view of many historians, the definitive end of the European colonial era, a moment in which control of a waterway determined the fate of empires. The patterns of water control did not end with formal colonialism. Modern development programs, trade agreements that require water privatization, and corporations that acquire water rights in poorer countries have been criticized as new forms of the same old pattern. The struggle over who controls water, who benefits from it, and who bears the cost of obtaining it is the same struggle that has been waged since the first empires arose along the Tigris and the Nile. The technology changes, the power dynamics endure. In the ruins of one of the great bathhouses of ancient Rome, completed around 216 of the Common Era, you can still walk across mosaic floors that once felt the bare feet of thousands of bathers. The complex covered roughly 27 acres and included not only hot, warm, and cold bathing rooms, but also gymnasiums, libraries, lecture halls, gardens, and shops. Water was supplied by a branch of the aqueduct, heated by an underground furnace system that circulated hot air beneath raised floors and through hollow walls. A visit to the baths was not merely an act of washing. It was a social ritual, a daily habit, and a statement about what it meant to be Roman. And it used prodigious amounts of water. The Romans were not the first people to build elaborate bathing facilities. The Great Bath of Mohenjo-Daro, which we explored earlier, is 2,000 years older. But the Romans were the first to make public bathing a universal civic service. By the 4th century, Rome alone had roughly 900 public baths. Admission was set so low that even the poorest citizens could afford it. The practice was so central to Roman identity that building a bathhouse was one of the first things any Roman governor did when establishing authority in a new province. When the Western Roman Empire fell in the 5th century, its bathing culture fell with it. The aqueducts that supplied the great bathhouses crumbled. The furnaces went cold. Over the centuries that followed, European attitudes toward bathing changed in ways that seem remarkable today. During the medieval period, public bathhouses did exist, and the Crusaders brought back some knowledge of Eastern bathing practices. But a combination of factors gradually eroded the bathing habit. The Black Death, which swept across Europe beginning in 1347, prompted authorities to close public bathhouses out of fear that the hot, moist air would open the body and let the plague in. This fear lingered for centuries. By the 1500s and 1600s, many European medical authorities actively warned against bathing, arguing that water weakened the body and made it vulnerable to disease. Instead of washing with water, the upper classes changed their linen undergarments frequently, believing that clean cloth would absorb the body's impurities. One French king is said to have bathed only 3 times in his adult life. Can you picture that? An entire continent, home to some of the wealthiest and most powerful people in the world, convinced for centuries that washing with water was actually dangerous. While Europe turned away from water, other civilizations maintained and even elevated their bathing traditions. The Turkish bathhouse, adapted from traditions the Ottomans inherited when they conquered Constantinople, became one of the defining institutions of Ottoman life. A typical visit followed a progression from a cool entry room through a warm transition room to a hot steam room, centered around a heated marble platform. Bathing was closely tied to the requirements of spiritual purity in Islam, making the bathhouse both a practical and a sacred space. The greatest Ottoman architect designed some of the finest examples, including one in Istanbul that has been in continuous operation since 1584. In Japan, the relationship between bathing and the natural world is among the most intimate on Earth. Japan sits on a volcanic ring, and its geology produces roughly 27,000 natural hot springs. The practice of bathing in these springs extends back at least 1,500 years. Over the centuries, hot spring bathing became deeply woven into Japanese culture, governed by careful etiquette and associated with ideas of spiritual purification, health, and the bonds of community. The neighborhood public bathhouse played a different but equally important role in Japanese life. Before private bathrooms became common in the 1960s, most city-dwelling Japanese bathed at their local bathhouse. At their peak, there were roughly 18,000 of these operating across the country. They were not just places to wash. They were community gathering spots, places where neighbors met, where gossip flowed, where the walls between social classes temporarily dissolved in the shared experience of sitting in hot water together. In Korea, large-scale public bathhouses that include hot tubs, cold pools, steam rooms, and communal sleeping areas became widespread in the 1990s and 2000s. These facilities operate around the clock and serve as gathering places, relaxation spots, and even informal hotels. They reflect a cultural ease with communal bathing that most Western societies have lost. The return of bathing to European culture was slow. The development of public health science in the 1800s, which demonstrated the link between cleanliness and disease prevention, gradually restored the reputation of water. Victorian reformers built public bathhouses in working-class neighborhoods, arguing that access to clean water for washing was a matter of public health. A law passed in Britain in 1846 gave local authorities the power to build public bathing facilities at public expense. The Victorian seaside resort represented another step in Europe's long road back to water. Sea bathing, initially prescribed as a medical treatment, became popular recreation by the early 1800s. But it was approached with extraordinary modesty. The bathing machine, a small wooden hut on wheels that could be rolled into the waves, allowed bathers to enter the water without being seen by people on the shore. The contrast with the communal nudity of Roman baths or Japanese hot springs could hardly be more stark. The private bathroom, which seems so natural and essential today, is a surprisingly recent invention. As late as 1900, the vast majority of homes in the United States and Europe did not have indoor plumbing or a dedicated room for bathing. The bathroom as a standard room in a new house became common only in the 1920s and 30s, driven by new plumbing technology, affordable fixtures, and determined marketing. Today, a typical shower uses roughly 80 liters of water. A bath uses about 150. These numbers multiplied across billions of people represent a huge share of total household water use. The luxury of unlimited hot water available at the turn of a tap is one of the most underappreciated achievements of modern life, and it is available to far fewer people than you might think. According to the World Health Organization, roughly 2 billion people worldwide still lack safe water services in their homes, meaning that the daily bath, so routine in wealthy nations, remains an impossible luxury for a quarter of humanity. The story of bathing is the story of our changing relationship with water and the body. It stretches from the communal pleasures of the Roman baths to the anti-washing fears of early modern Europe, from the spiritual warmth of the Japanese hot spring to the stubborn inequality that denies clean water to billions. It reminds us that water is not only something to drink and a resource to manage. It is, and always has been, the way we care for ourselves and for each other. In August of 1519, Ferdinand Magellan sailed from Spain with 5 ships and roughly 270 men on what would become the first voyage around the world. Among his most critical supplies were wooden casks of fresh water, stored below decks alongside barrels of wine and salted food. Magellan knew, as every sailor of his era knew, that fresh water was the factor that most often determined whether a voyage ended in triumph or in death. A ship could carry enough dried food for months if it was properly preserved. But water, stored in wooden casks in the suffocating heat below decks, began to go bad within weeks. Green things grew in it. It turned brown and thick and developed a smell so foul that sailors could barely force themselves to swallow it. Men weakened by bad water fell easy prey to disease, and dehydration killed faster than starvation. When Magellan's fleet crossed the Pacific in the winter of 1520 and 1521, a crossing that took more than 3 months, the water supply failed catastrophically. The men were reduced to drinking water so rotten they had to hold their noses to get it down. They soaked leather strips in seawater to soften them and chewed them for moisture. They spread their sails to catch rain whenever it fell. 19 men died during the crossing. The paradox of life at sea, that sailors were surrounded by an ocean of water that would kill them faster than thirst, was the defining challenge of maritime history. The standard water ration on a European sailing ship was roughly 2 liters per person per day. This had to cover both drinking and cooking, and it was never enough in the heat of the tropics where a working man could sweat out several liters in a single day. A large warship carrying hundreds of men needed vast quantities. The casks took up enormous cargo space and were extremely heavy, affecting how the ship handled in the water. Water storage technology evolved slowly. The earliest ships used clay jugs or leather bags, both of which leaked and broke down. Wooden casks became the standard, but wood gave the water a taste. The seams could open and drip, and the warm darkness inside the barrel was the perfect home for things you did not want growing in your drinking water. Some navies added vinegar or wine to slow spoilage. Others mixed the water with beer or rum, a practice that served the double purpose of making bad water drinkable and keeping morale from collapsing entirely. The British Navy's daily issue of rum, which continued until 1970, had its origins in the very practical need to make stored water tolerable. It was not until the early 1800s that the Royal Navy began replacing wooden casks with iron tanks. Iron did not add flavors, did not leak through seams, and could be shaped more efficiently to fit the hull. The tanks were a real improvement, though the water inside was only as clean as the place it had been drawn from on shore. Rainwater collection was a critical backup on long voyages. Sailors rigged canvas sheets or used the sails themselves to funnel rainwater into barrels. The first few minutes of rain were usually discarded because the sails would be coated with salt spray, and drinking even small amounts of salt water was known to speed up dehydration and hasten death. Once the sails were rinsed clean, the collected water was relatively pure and could extend the ship's supply by days or even weeks. The Polynesian navigators who crossed thousands of miles of the Pacific in open canoes long before Europeans ventured beyond sight of land solved the freshwater problem in their own ways. They carried water in sealed bamboo tubes and hollowed-out gourds. They could taste the difference between ocean currents fed by rainfall and those that were purely salty. Their navigational knowledge, passed down through oral tradition, included detailed information about which islands had freshwater springs. This knowledge was as vital to their survival as their ability to read the stars and the waves. The development of desalination at sea, the ability to turn ocean water into something drinkable, was one of the great advances in maritime life. The principle of distilling salt water, boiling it and collecting the fresh steam, was known in ancient times. But practical shipboard distillation equipment was not available until the 1700s and 1800s, when copper stills became compact enough to produce useful amounts of fresh water on board. The invention of the steam engine changed things profoundly. Steam-powered ships could use the heat from their boilers to distill seawater as a byproduct of their engines, and by the late 1800s, most steamships had equipment that could produce thousands of gallons of fresh water per day. Ships were freed from their dependence on freshwater ports, and the range of sea travel expanded dramatically. Modern nuclear-powered submarines represent the ultimate answer to the freshwater problem at sea. A nuclear submarine can remain underwater for months, and its reactor provides virtually unlimited energy for turning seawater into drinking water. The crew drinks water that was ocean water just minutes before, clean to standards exceeding most city water supplies. The submarine also generates its own oxygen by splitting water molecules apart, making water the source of both drinking water and breathable air in one sealed environment. The control of freshwater ports and resupply stations has shaped naval strategy since ancient times. One of the reasons the British Empire maintained bases from the Mediterranean to the Indian Ocean to Southeast Asia was to ensure that its navy always had access to fresh water. Controlling the water supply at a port could determine the outcome of a campaign. During one famous siege, the survival of the defenders depended on their ability to protect their freshwater supply, and the tunnels they dug to safeguard it can still be seen today. Water at sea has always been a matter of life and death in a way that is hard to appreciate from dry land. Every explorer, every naval commander, every common sailor who set out across the ocean knew that the endless water stretching to every horizon was poison to a thirsty human being. The history of maritime exploration is, in many ways, the history of solving a single problem: how to carry enough drinkable water to survive the crossing. It shaped the routes of exploration, the design of ships, the strategy of empires, and the fate of millions of men who staked their lives on wooden casks of water that might or might not last until the next port appeared on the horizon. In 1789, a French nobleman traveling near the shore of Lake Geneva stopped to drink from a spring at the base of a mountain range. He was suffering from ailments of the liver and kidneys, and the water, he later reported, brought him remarkable relief. Word of the spring's supposed healing properties spread among the French aristocracy, and within a few decades the water was being bottled and sold under the name of the nearby village, Evian. 2 centuries later, that spring produces roughly 6 million bottles of water every day and earns over €1 billion each year. The water that once eased a nobleman's discomfort has become one of the most profitable consumer products on Earth. And the story of how that happened is a story about marketing, fear, vanity, and the transformation of a free natural resource into a $350 billion global industry. The idea of bottling and selling spring water is not a modern invention. The European spa town tradition stretches back centuries. Springs rich in dissolved minerals were believed to treat everything from gout to nervous complaints. And by the 1600s and 1700s, European aristocrats made regular pilgrimages to places like Bath in England and Baden-Baden in Germany to take the waters. By the 1700s, entrepreneurs began bottling spa water for customers who could not make the journey themselves. For most of the 20th century, bottled water remained a niche product, bought mainly by the wealthy or by people with genuinely poor tap water. In the United States and most of Europe, municipal water supplies were widely trusted and widely used. Bottled water was a tiny corner of the beverage market. The transformation began in the late 1970s and accelerated through the 80s and 90s. Several things happened at once. Lightweight plastic bottles replaced heavy glass, making it possible to sell water anywhere, from corner shops to vending machines to sports stadiums. At the same time, a series of water contamination scares eroded public confidence in tap water, and clever marketing demonstrated that water could be sold not merely as a drink but as a lifestyle choice, a symbol of health and sophistication. By the 1990s, the major beverage companies recognized the enormous profit potential. Two of the world's largest soft drink makers launched their own bottled water brands, both of which were, and still are, purified municipal tap water, run through extra filtering and sometimes enhanced with minerals for taste. The profit margins were extraordinary. The water itself was essentially free. The plastic bottle cost a few cents to make, and the retail price was comparable to or higher than a bottle of soda. The marketing was brilliantly effective. Bottled water brands wrapped themselves in images of mountain springs, glaciers, pristine forests, and ancient geological formations, creating an association with natural purity that often bore little relationship to where the water actually came from. One famous brand featured a tropical island on its label and the slogan "Untouched by Man," even though the water was pumped from an underground source, processed in a factory, packaged in plastic made from petroleum, and shipped thousands of miles across the ocean. The environmental consequences have been severe and are getting worse. An estimated 1 million plastic bottles are bought around the world every single minute, and the majority are not recycled. In the United States, roughly 70% of plastic water bottles end up in landfills, incinerators, or the environment. Globally, the numbers are even worse. Plastic bottles that enter rivers and oceans eventually break down into tiny particles called microplastics, which now contaminate every ocean, every river system, and every food chain on the planet. Here is an irony worth pausing on. Many people buy bottled water because they believe it is purer than what comes from the tap. But research has found that numerous chemicals can leach from the plastic bottle itself into the water it contains. Meanwhile, in most wealthy countries, tap water is tested far more frequently and held to stricter standards than bottled water. An extensive review found that a significant portion of bottled water brands contained impurities exceeding health guidelines. The bottled water industry has also created conflicts over water access in the communities where it operates. In several places, large companies have been criticized for extracting millions of gallons of groundwater under permits that cost almost nothing, while local residents face water shortages. In one town in France, where a major company has bottled local spring water for decades, the underground water level has dropped so far that the town now plans to bring in water from elsewhere, effectively importing water so that a corporation can continue exporting it. The pushback has been growing. Several cities and universities have banned single-use plastic water bottles. Refillable bottle culture has expanded. Public water fountains, long neglected, are being rebuilt in some places. And in 2010, the United Nations formally recognized access to clean water as a human right, challenging the idea that water should be treated purely as a product to be bought and sold. But the industry continues to grow, driven by rising demand in countries where tap water is genuinely unsafe. In China, India, and across Africa, bottled water is not a lifestyle choice. It is a survival necessity for hundreds of millions of people who cannot trust what flows from their pipes. For these consumers, the question is not whether bottled water is sustainable. It is whether it is the only safe option they have. The story of bottled water is, in small, the story of water itself, a substance essential to life, free in nature, transformed by human systems of commerce and inequality into a commodity that costs the poor the most and enriches the already wealthy. It is a story in which the most common compound on the surface of our planet has been packaged, branded, and sold back to the very species that cannot survive without it, at a markup of roughly 3,000% over the cost of tap water, in a container that will last in the environment for about 450 years. In 1596, a courtier, poet, and godson of Queen Elizabeth I of England published a peculiar little book. It was ostensibly a satirical pamphlet, its title a pun on a common slang word for the toilet. But buried within the jokes was something genuinely new, a detailed description, complete with diagrams, of a device its author called a water closet, a flushing toilet. The design consisted of a deep, oval bowl sealed with a mixture of pitch and resin fed by water from a tank upstairs. When a valve was opened, water rushed in, carrying the contents down into a chamber below. Each flush used about 7.5 gallons. The inventor, a man named Sir John Harrington, built a working version at his home near Bath and reportedly made a second for his godmother, the Queen herself. She is said to have used it but found it too noisy. Harrington's invention was clever, but it was impractical for widespread use. Without a sewer to receive the flushed waste, the toilet simply moved the problem from the bowl to a pit, which still had to be emptied by hand. Without piped water, the tank had to be filled manually. And without any understanding that germs in water cause disease, there was no urgency to adopt the technology. The flush toilet remained a curiosity for nearly 200 years. The reinvention came in 1775, when a Scottish watchmaker patented an improved design with a crucial innovation, a curved section of pipe that kept a standing pool of water between the bowl and the drain, blocking the foul sewer gases from rising back into the room. This simple piece of plumbing solved the worst problem with early toilets, the smell, and made the device genuinely usable as furniture for the home. The man whose name is most associated with the toilet, Thomas Crapper, did not actually invent it. This is perhaps the most widely believed false credit in the history of technology. Crapper, born in 1836, was a plumber who held several patents for improvements to the toilet, including a better version of the floating mechanism that controls the water level in the tank. His most important contribution may have been commercial rather than technical. He opened one of the first showrooms for bathroom fixtures in London, displaying his products in shop windows at a time when such items were considered too embarrassing for public view. The popular link between his name and the toilet is reinforced by a common slang term, but that word actually predates Crapper by centuries. Before the flush toilet, the vast majority of humanity dealt with waste through methods ranging from the sophisticated to the unthinkable. The Indus Valley civilization had flush latrines connected to covered drains more than 4,000 years ago. The Romans built public facilities where citizens sat side by side on stone benches, their waste washed away by a constant stream of water beneath the seats. Medieval castles had small chambers built into exterior walls, from which waste dropped down into the moat or a pit below. For the urban poor of the 1800s and 1900s, the outhouse built over a cesspit was the standard, often shared among dozens of families. The workers who emptied these pits labored through the night in conditions almost beyond modern imagination. The contents were carted through the streets and dumped outside the city or sold as fertilizer. The widespread adoption of the flush toilet in the 1800s was made possible by three things coming together at the same time: factory-made ceramic fixtures, piped city water, and city sewer systems. Without all three, the flush toilet was either impractical or actually made things worse. As we explored in the story of the Great Stink, the adoption of flush toilets in London before a proper sewer system existed actually sped up the contamination of the Thames, turning a bad situation into a crisis. The flush toilet uses, and continues to use, a great deal of water. Early models consumed as much as 13 litres per flush. Modern low-flow designs use about 6, and the most efficient versions can work with as little as 3. But even at 6 litres, a family of 4 flushing 5 times each per day uses about 120 litres of perfectly good drinking water just to carry waste away, roughly a quarter of a typical household's total water use. This has sparked growing interest in waterless and composting toilet technologies that break the link between sanitation and water use altogether. The global picture in the 21st century is sobering. As of recent counts, roughly 3.5 billion people worldwide, more than 40% of the global population, still lack access to safely managed sanitation. Hundreds of millions of people have no toilet at all. Every day, hundreds of children under the age of 5 die from diseases directly linked to unsafe water and poor sanitation. The economic case for investing in toilets is overwhelming. Every dollar spent returns several dollars in reduced healthcare costs, increased productivity, and better educational outcomes. The United Nations has called for universal access to proper sanitation by 2030. As of the mid-2020s, no region of the world is on track to meet that goal. The toilet, the most humble and taken for granted fixture of modern life, remains one of the most unequally distributed technologies on the planet. A major foundation launched a challenge in 2011 to reinvent the toilet, funding research into sanitation systems that do not need sewer connections, piped water, or outside energy. The resulting designs, including toilets that process waste into fertilizer, fuel, or reusable water, could represent a change as significant as Harrington's original device. The history of the toilet is the history of our most intimate relationship with water. It is a history most people prefer not to think about, which is precisely why it matters. Every improvement in toilet technology, from the drains of Mohenjo-Daro to the waterless prototypes of today, has been an improvement in public health, in dignity, and in the basic quality of human life. It is a quiet revolution, one that has saved more lives than any war and improved more daily experiences than any other invention. And for billions of people around the world, it is a revolution that has yet to arrive. In 1684, a Belgian engineer completed one of the most extraordinary machines of the pre-industrial world. It was a vast apparatus built on the banks of the Seine River just west of Paris, designed to solve a problem that had obsessed the French King Louis XIV. How could water be delivered to the 1,400 fountain jets of the Palace of Versailles, which sat on a plateau far from any natural water source, high above the river below? The solution consisted of 14 enormous water wheels, each 12 meters across, driving over 200 pumps that lifted water from the river through a system of pipes and intermediate stations up to a hilltop reservoir. At its peak, the machine could deliver roughly 5,000 cubic meters of water per day. The noise of its operation could be heard for miles. And it was still not enough. The fountains of Versailles needed roughly 4 times as much water as the machine could provide. The Sun King, who had insisted on building his palace in this water-poor location despite being advised to build elsewhere, was forced to accept that his fountains could not all run at the same time. Instead, a team of fountain attendants developed a system of whistled signals to alert one another as the king walked through the gardens. They turned on the fountains just ahead of him and shut them off behind him, creating the illusion that all 1,400 jets were running continuously. The supreme expression of royal power through water was, in truth, an elaborate stage trick. The fountains of Versailles were the culmination of a tradition reaching back to antiquity. The Romans built fountains throughout their empire, and the tradition was revived during the Renaissance in Italy, where the great fountain designers of the 1500s and 1600s created works that transformed public space. One of the most famous, a fountain in a Roman square completed in the mid-1600s, features 4 colossal figures representing the great rivers of the 4 known continents, each carved with extraordinary energy and grace. The Trevi Fountain, completed in 1762 and fed by a restored Roman aqueduct, has become one of the most visited monuments in the world. In these works, water is not merely present. It is the active medium of artistic expression. The play of light on moving water, the sound of cascading jets, the mist that catches the sun and creates fleeting rainbows, all of these are part of the art itself. The sculptor shapes the stone, the architect designs the basin, but the water, in its movement and its music, completes the work. Water has been a subject of art for as long as art has existed. The earliest known images of water appear in cave paintings and rock carvings, where wavy lines and zigzag patterns are believed to represent rivers and rain. In ancient Egypt, tomb paintings depicted the Nile and its marshes with careful attention to the details of fish, birds, and reeds. In Chinese painting, the tradition known as mountain water made water one of the 2 fundamental elements of landscape art, balancing the solidity of mountains with the flow and impermanence of water. The Islamic garden tradition used water as both artistic medium and spiritual symbol. The 4-channel garden, with flowing water representing the rivers of paradise, created spaces of extraordinary beauty and meaning. The reflecting pools of the Alhambra and the Taj Mahal use perfectly still water as a mirror, doubling the visual impact of the buildings and creating a sense of infinite depth and symmetry. In Japanese art, water reached perhaps its most widely known expression in a woodblock print created around 1831 by Katsushika Hokusai. The print shows an enormous wave, its crest breaking into claw-like fingers of foam, towering over tiny fishing boats with a distant mountain diminished in the background. The composition captures the terrifying power and beauty of water in a single frozen instant, and it has become the most recognized work of Japanese art in the Western world. Hokusai's wave had a profound influence on European art through the movement that brought Japanese aesthetics to Western attention in the late 1800s. Claude Monet, who collected Japanese prints and hung them throughout his home at Giverny, spent the last 3 decades of his life painting the water garden he had built there. He diverted a small stream to create a pond, planted it with water lilies, and then painted it over and over, in every kind of light, in morning mist and afternoon heat, in autumn gold and winter grey. Monet was not really painting water lilies. He was painting the act of seeing itself, the way light plays across a water surface, the way reflection and depth and color shift from one moment to the next. His final water lily paintings, vast curved panels installed in a museum in Paris according to his own design, surround the viewer in an immersive panorama of sky, water, and floating blossoms. They anticipate modern installation art by half a century, and their subject at its deepest level is simply water. The relationship between water and music is equally rich. The sound of flowing water has been used by composers across cultures, from orchestral works that evoke rivers and seas to the contemporary use of recorded water sounds in music designed for relaxation and sleep. There is something about the sound of water that is inherently calming to most people, a response that psychologists think may be connected to our deep association between the sound of water and the nearness of a life-sustaining resource. In contemporary art, water has become a subject that speaks to environmental crisis. Large-scale installations have used thousands of liters of water per minute to create temporary waterfalls in urban settings, drawing attention to the relationship between cities and the water that surrounds them. Other artists have used still pools and flowing streams to address themes of memory, loss, and the passage of time. Water in art serves a purpose that water in engineering and politics does not. It reminds us of beauty. In a world where water is increasingly discussed in terms of scarcity, conflict, and crisis, the artistic tradition reminds us that water is also the source of contemplation, the medium of aesthetic pleasure, and the element that connects our senses to the natural world more than any other. The fountains of Rome, the wave of Hokusai, the water lilies of Monet, the sound of a stream in the forest. These are not distractions from the serious business of managing water. They are reminders of why the effort to protect it is worth making in the first place. Sometime around 1508, in a studio in Florence, Leonardo da Vinci sat before a sheet of paper and drew water. Not a river, not a fountain, not a basin, but water itself. The way it moves, curls, crashes, and recombines. The page, now preserved in a royal collection in England, is covered with detailed studies of water flowing around obstacles, forming spirals, crashing into pools. Leonardo was fascinated by water in a way that went beyond any practical use. He filled thousands of pages in his notebooks with observations, from the patterns of erosion on riverbanks to the way rain fell on different surfaces. He was, by some accounts, the first person to study water not merely as something to use, but as something to understand. And yet Leonardo, for all his brilliance, got the water cycle wrong. Influenced by ancient ideas that rivers were fed by vast underground reservoirs connected to the sea, he believed that water rose through the earth by some mysterious process and emerged from mountain springs, flowed down to the sea, and then returned underground to begin the cycle again. The correct explanation that rivers are fed by rain, which comes from the evaporation of surface water, was not something Leonardo could accept. It seemed to him that rainfall alone was not enough to account for the enormous volumes of water flowing in rivers. The water cycle is one of the most fundamental processes on Earth, and it is remarkable how long it took humanity to understand it correctly. The basic idea that water evaporates from the surface, rises as vapor, forms clouds, falls as rain, and flows back to the sea seems obvious in hindsight. But for most of recorded history, where rivers and springs came from was a genuine mystery. The ancient Greeks proposed various explanations. Aristotle suggested that water vapor was drawn underground by the cold of subterranean caverns, where it condensed to feed springs. Plato imagined a vast underground reservoir. The Roman philosopher Seneca proposed that water was created inside the earth from the transformation of air in cavities. These ideas persisted for nearly 2,000 years, accepted by scholars who trusted the authority of ancient texts over what they could see with their own eyes. The breakthrough came in the 1600s, driven by a simple but revolutionary idea: measure things. In 1674, a French lawyer with scientific interests calculated the rainfall over the basin of the Seine River and compared it with the river's discharge. His measurements showed that rainfall was roughly 6 times greater than the river's flow, meaning that rain alone was more than enough to account for the water in the river. The underground reservoir theory was unnecessary. A French physicist confirmed and extended this work by measuring the Seine's flow over several years and showing that it matched the patterns of rainfall in the region. His measurements were more precise and provided stronger evidence that rivers were simply rainwater finding its way downhill. The final piece of the puzzle was provided by an English astronomer better known for the comet that carries his name. In 1687, Edmund Halley estimated the amount of water vapor that the sun lifted from the surface of the Mediterranean Sea each day. By measuring evaporation from a heated pan of water and scaling up to the area of the entire sea, he calculated that the sun evaporated billions of tons of water daily, enough to account for all the rivers flowing into the Mediterranean. He had demonstrated the evaporation half of the cycle as convincingly as the French researchers had demonstrated the rainfall half. Together, they had established the modern understanding of the water cycle. Water evaporates from the surface, condenses in the atmosphere, falls as rain or snow, collects in rivers and lakes, and returns to the sea. The most important thing this understanding revealed is that Earth's water is a closed system. No new water is being made. No old water is being lost. The water you drink today may contain molecules that floated in ancient seas, fell as rain on the Roman Empire, or passed through the body of a dinosaur millions of years ago. The total amount of water on Earth, roughly 1.5 billion cubic kilometers, has stayed essentially the same for billions of years. It simply moves endlessly between the ocean, the air, and the land. The science of understanding how water moves through the Earth, known as hydrology, grew steadily in the centuries that followed. A French engineer working in the 1850s conducted experiments on how water flows through beds of sand, producing a fundamental equation that governs groundwater movement. In the United States, a one-armed Civil War veteran named John Wesley Powell explored the Grand Canyon and became one of the first scientists to map the water resources of the American West and to warn that the region's dryness placed strict limits on how many people could live there. His warnings were largely ignored, with consequences that are painfully obvious today as rivers run dry and reservoirs empty. The 20th century brought powerful new tools. Radioactive traces from nuclear testing in the 1950s and 60s allowed scientists to determine how long water had been underground and how quickly underground water sources refilled. Satellites launched starting in the 1960s made it possible to observe the water cycle on a global scale for the first time, tracking moisture through the atmosphere, measuring rainfall patterns, and monitoring changes in ice sheets and sea levels. Today, the science of hydrology faces its greatest test, predicting how the water cycle will respond to a warming climate. The basic physics are clear. A warmer atmosphere holds more moisture, which should make both evaporation and rainfall more intense. But the details are enormously complicated. Some places will get wetter, others will get drier. The timing of snowmelt will change. Glaciers that feed rivers will shrink. The ancient rhythms of rain and drought that farmers have relied on for millennia are shifting in ways that are difficult to predict and impossible to reverse on any human timescale. The water cycle is the engine that drives everything we have explored in this entire story, from the first rains on the young Earth to the modern water crisis. It is the mechanism by which water moves from ocean to cloud to river to tap to drain to ocean again, an endless circulation that has continued without interruption for billions of years. Understanding it took humanity thousands of years of wrong guesses, followed by a few decades of careful measurement. Protecting it, in a world being reshaped by human activity, may take everything we have. In the 1st century before the Common Era, the Roman architect Vitruvius described a machine that would become one of the most important inventions in human history. It was simple enough. A vertical water wheel turned by the current of a stream was connected through a set of gears to a horizontal millstone. Grain was poured between the stones, and the force of falling water did the work that had previously required the muscles of people or animals. It was not the first watermill. Evidence suggests that water-powered mills existed in the Mediterranean world and in China by at least the 3rd century before the Common Era. But Vitruvius gave us the first detailed technical description of how such a machine worked, and it established the watermill as a recognized tool of civilization. The Romans did not exploit water power as fully as they might have, partly because the widespread use of enslaved labor reduced the incentive to build machines. But by the later years of the empire, watermills had become common. The most striking example was a complex of 16 mills built on a hillside near the city of Arles in southern France, arranged in 2 parallel rows and fed by a branch of the Roman aqueduct. These mills could reportedly grind enough grain to feed the entire city. The site represents one of the earliest examples of water power used on an industrial scale. It was during the medieval period that water power truly transformed Europe. A great survey compiled for the English king in 1086 recorded over 5,600 watermills in England alone. By the 12 and 1300s, watermills were grinding grain, processing cloth, sawing wood, hammering metal, powering bellows, and doing dozens of other kinds of heavy work. The great monasteries, which combined spiritual devotion with practical engineering, developed especially sophisticated water-powered complexes where a single stream served the forge, the kitchen, the latrines, and the fish ponds in an integrated system. The economic importance of watermills is hard to overstate. They were among the most valuable properties in medieval Europe, and the right to operate one was tightly controlled by feudal lords, who charged fees to peasants required to use the lord's mill rather than grinding their own grain. The monopoly of the mill was a source of wealth and resentment alike, and disputes over milling rights were among the most common legal conflicts of the era. The transition from the water wheel to the water turbine in the 1800s was a quiet revolution that helped power a much louder one. The traditional water wheel, whether turned by water flowing beneath it or falling onto it from above, was relatively inefficient, converting perhaps 20 to 40% of the water's energy into useful work. In 1826, a French engineer developed the first practical water turbine, an enclosed device where water flowed through curved blades, transferring its energy far more efficiently. His turbine achieved efficiencies above 80%, roughly double the best water wheels. In 1848, an American engineer improved the design further, creating a turbine that could achieve efficiencies above 90% and adapt to a wide range of water conditions. This design remains the most widely used water turbine in the world today, installed in power plants from the Hoover Dam to the Great Dam on the Yangtze. The direct link between water power and electricity was forged on September 30th, 1882, when a small plant in Appleton, Wisconsin began generating electrical power using a water turbine driven by a local river. It was the first hydroelectric power plant in the world, producing roughly 12 kilowatts, enough to light a few buildings. The amount of power was tiny, but the principle was established. Falling water could spin a turbine, the turbine could spin a generator, and the generator could produce electricity. The moment that changed everything came in 1895, when Nikola Tesla and George Westinghouse completed a power plant at Niagara Falls. The plant used Tesla's alternating current system, which could carry electricity efficiently over long distances, something that the competing system of Thomas Edison could not do. On a November day in 1896, electrical power generated by Niagara Falls was sent over 20 miles to the city of Buffalo, lighting its streets and running its streetcars. It was the first long-distance transmission of hydroelectric power, and it proved that water's energy could be turned into electricity and delivered to cities far from the source. The impact was revolutionary. Within decades, hydroelectric dams were being built on rivers around the globe. Today, water power generates roughly 16% of the world's electricity and about 60% of all renewable energy. It is the oldest and most established form of renewable power, and it remains one of the cheapest. But the environmental costs are real. Large dams block the journeys of fish, particularly salmon, which must travel upstream to lay their eggs. The lakes behind dams flood valleys, displace communities, and destroy ecosystems. Stagnant reservoir water can release methane, a potent greenhouse gas, especially in tropical regions where drowned vegetation decays. The sediment that rivers naturally carry to coastlines is trapped behind dams, causing erosion downstream and the loss of fertile land. The newer frontiers of water power seek to capture energy from moving water without the damage caused by large dams. Tidal power, which uses the rhythm of the tides, has been operational since the mid-1960s, when a facility in France began generating electricity from tidal flows. Wave energy technology, which captures the motion of ocean waves, is still mostly experimental but holds real potential for island nations and coastal communities. Smaller run-of-river systems divert part of a river through a turbine without building a large dam, offering a lower impact way to generate clean electricity. The story of water power is the story of humanity learning to let water do the heavy work. From the first watermill grinding grain in a Roman village to the massive turbines generating electricity for millions of homes, the principle has remained the same. Water flows downhill, and that flow contains energy that can be captured and used. It is the most ancient of renewable energy sources, older than windmills by centuries and older than solar panels by millennia. The challenge of the 21st century is to keep harvesting that energy while allowing the rivers themselves to remain alive. In the early 2000s, Israel was running out of water. The country's main freshwater lake had dropped to dangerous levels. The coastal underground water source was being pumped too fast and increasingly contaminated by salt water creeping in from the sea. Farming was threatened. A rationing was imposed. Climate scientists delivered a grim assessment: the worst drought in over 900 years, and likely to get worse. A country founded on the ideal of making the desert bloom was confronting the possibility that it might bloom no more. Within a decade, Israel had transformed itself from a nation on the edge of water disaster into one with a surplus. The instrument of this transformation was the ability to turn seawater into drinking water. Beginning in 2005, the government built a series of massive treatment plants along the Mediterranean coast, each one capable of converting millions of cubic meters of seawater into fresh water every year. By 2022, roughly 86% of Israel's household drinking water came from the sea. A country that had fought wars partly over access to rivers and lakes had largely freed itself from depending on them. The idea of making seawater drinkable is ancient. Aristotle described the basic principle in the 4th century before the Common Era, noting that when seawater is heated and the steam is collected, the result is fresh water. Sailors practiced crude versions of this at sea for centuries, boiling seawater over the galley fire and catching the steam on cold surfaces. Thomas Jefferson approved the printing of instructions for doing this aboard every American naval ship, but producing enough fresh water to supply cities and farms remained impractical until the 20th century. The first large-scale plants used a process in which seawater was heated and then passed through a series of chambers at progressively lower pressures. At each stage, some of the water flashed into steam, which was then collected as fresh water. The technology was energy-hungry but reliable, and it became the foundation of water production in the oil-rich Gulf states, where energy was cheap and fresh water was scarce. Saudi Arabia, which today produces roughly 22% of the world's desalinated water, built many of its early plants this way. The real revolution came with a different approach, one that does not rely on heat at all. Instead, seawater is pushed through a special membrane at very high pressure. The membrane allows water molecules to pass through but blocks the salt. The result is fresh water on one side and concentrated brine on the other. The key breakthrough was made in the late 1950s and early 60s by a researcher working at the University of California, who developed the first practical membrane thin enough to make this process affordable. The first commercial plant using this technology opened in California in 1965, treating salty groundwater rather than full seawater. Seawater plants followed in the 1970s, and the technology has been steadily improving ever since. Modern plants using this membrane technology are dramatically more energy efficient than the heat-based methods they have largely replaced. The theoretical minimum energy needed to clean seawater is about 1 unit of electricity per cubic meter. Today's best plants achieve roughly 3 to 4 times that minimum, a remarkable improvement from the 20 or more units required by older methods. Devices that capture the pressure energy of the leftover brine and recycle it to push more incoming seawater have been crucial to these gains. The environmental concerns are real and worth taking seriously. The concentrated brine discharged by these plants, roughly twice as salty as the seawater taken in, can harm ocean life if not handled carefully. The chemical cleaners used in the process need responsible disposal. And the energy required, even at modern efficiency levels, means that a plant powered by coal or gas is contributing to the very climate change that is making fresh water scarcer. The ideal solution, and one that is increasingly being pursued, is to power these plants with solar energy, which is abundant in exactly the sunny, dry regions where the need for fresh water is greatest. This technology is now a global industry worth tens of billions of dollars a year, with roughly 21,000 plants operating in more than 170 countries. The largest markets are in the Middle East, North Africa, and Australia, but the technology is expanding rapidly into water-stressed parts of Europe, the Americas, and Asia. Singapore, a city-state with almost no natural fresh water, gets about a quarter of its supply this way and plans to increase that share significantly. The cost has fallen sharply but remains higher than traditional water sources. In Israel, desalinated water costs roughly 50 to 60 cents per cubic meter compared to about 20 cents for naturally available water. For farming, which uses the majority of water in most countries, the economics are still challenging. But as natural sources dwindle and the cost of the technology keeps falling, the crossover point where turning seawater into fresh water becomes the cheapest option is approaching rapidly in many regions. Researchers are working on the next generation of technologies that could reduce costs even further. New types of membranes inspired by the natural filtering proteins found in living cells, and systems that use natural differences in saltiness rather than mechanical pressure are all being explored. If any of these achieves commercial scale, it could make the technology affordable enough to serve even the poorest communities. This ability to make fresh water from the ocean does not by itself solve the water crisis. It is no substitute for conservation, for protecting the rivers and aquifers we already have, or for addressing the inequality that leaves billions of people without water that is already available somewhere. But it represents something no other technology offers: the ability to tap into the practically limitless supply of the oceans. In a world where rising populations, growing economies, and changing climates are placing unprecedented pressure on the fresh water we have, the ability to drink the sea may prove to be one of the most consequential achievements in all of human history. In 2012, a man in the state of Oregon was sentenced to 30 days in jail. His crime was collecting rainwater on his own property. He had built 3 reservoirs on his 170 acres that captured water from snowmelt and rainfall, holding a total of roughly 13 million gallons. Under state law, all water, including rain, was classified as a public resource, and the man had not obtained the required permits. He had been fighting the state over the issue for more than a decade, arguing that water falling from the sky onto his own land should be his to keep. The state disagreed, and the courts upheld the conviction. The case generated considerable attention and outrage, and it illustrated a question that most people never think about until it affects them personally: who owns the water? The answer turns out to be one of the most complicated and consequential questions in the history of law, and it has been answered differently by every civilization, every legal tradition, and every era. The earliest water laws were part of the first legal codes. The laws of Babylon, written roughly 1750 years before the Common Era, contained rules about maintaining irrigation canals and the responsibility of farmers whose carelessness caused flooding on a neighbor's field. Roman law developed the idea that flowing water was a common resource that could not be privately owned. Citizens could use river and stream water for drinking, bathing, and farming, as long as they did not unreasonably interfere with the rights of others. This principle of shared reasonable use became the foundation for the legal approach that would later develop in English law and spread across much of the world. This approach, sometimes called the riparian doctrine, holds that people who own land next to a body of water have the right to make reasonable use of it. The water itself is not owned by anyone. It is shared, and each user may draw from it as long as they do not reduce its quantity or quality unreasonably for others. This works well enough in places where water is plentiful. It breaks down where water is scarce. The American West developed a fundamentally different system. During the California gold rush of the 1840s and 50s, miners needed water to wash gold from gravel, and the streams they needed were often far from their claims. The Eastern system would have limited water use to people who owned land along the stream. Instead, the miners invented a first-come, first-served approach. The first person to take water from a stream and put it to use acquired a right to that water that was superior to everyone who came later, regardless of where they lived. This principle became the legal foundation for water across the Western states. The Western system created water rights that could be bought, sold, and traded separately from the land, turning water into a tradable commodity. In times of shortage, the oldest rights were satisfied first, and newer users received nothing at all. The system also encouraged maximum use, since a right that was not exercised could be taken away under the principle of use it or lose it, creating a perverse incentive to consume rather than conserve. Islamic legal tradition developed its own sophisticated framework for water. Water was considered a gift from God, and no individual could own it. The right of thirst guaranteed that no person or animal could be denied drinking water, regardless of property lines. More detailed rules governed the sharing of irrigation water, typically based on the size of the land and its distance from the source. And as we have seen, the charitable foundation system funded public water infrastructure as an act of religious duty. The modern era has seen an intense global debate over whether water should be treated as a public good or a private commodity. In the 1990s and 2000s, international financial institutions frequently required developing countries to privatize their water systems as a condition of receiving loans. The results ranged from mixed to disastrous. The Cochabamba water war in Bolivia was the most dramatic example of the backlash, but similar protests erupted in South Africa, the Philippines, and elsewhere. One country took water privatization further than any other. Under a law enacted during a military dictatorship in the early 1980s, water rights were completely separated from land and treated as freely tradable private property. Companies and individuals could buy, sell, and speculate in water rights without restriction, and there was no requirement that the water actually be used. The result was a concentration of water rights in the hands of large corporations, while small farmers and indigenous communities were left without enough water for their needs. On the 28th of July 2010, the United Nations General Assembly adopted a resolution explicitly recognizing access to clean water and sanitation as a human right, essential to the full enjoyment of life. The resolution passed with 122 votes in favor and none against, though 41 countries abstained, including several of the wealthiest nations, which expressed concerns about the legal implications. The tension between water as a right and water as a commodity remains unresolved. Those who favor water markets argue that pricing water at its true value encourages efficient use and investment in conservation. Those who see water as a fundamental right argue that subjecting a survival necessity to market forces condemns the poor to thirst while the wealthy water their gardens. Both sides have evidence to support their positions, and the debate shows no sign of ending soon. The question of who owns the rain is, in the end, a question about what kind of world we want to live in. It is about whether the substance that every living being needs to survive should be distributed by markets, by governments, by communities, or by some combination of all three. It is a question that the people of Babylon wrestled with 4,000 years ago, and it is a question that the people of California, India, Bolivia, and 100 other water-stressed places wrestle with today. The answer has never been simple, and the stakes have never been higher. In 1960, the Aral Sea was the fourth largest lake in the world. It lay in the heart of Central Asia, straddling the border between Kazakhstan and Uzbekistan, covering an area larger than the Republic of Ireland. Its waters, fed by two great rivers flowing down from the mountains, supported a thriving fishing industry that employed tens of thousands of people. A port city on its southern shore processed enormous quantities of fish each year, and its canning factories shipped products across the entire Soviet Union. The Aral Sea was a living ecosystem, a source of livelihood, and a gentling influence on the harsh climate of the surrounding steppe. Then the Soviet government decided to grow cotton. Beginning in the 1960s, under central planning orders that prioritized self-sufficiency, the authorities massively expanded cotton farming in the surrounding republics. Cotton is one of the thirstiest crops in the world, and the water to feed the new fields came from the two rivers that fed the sea. Vast canal networks, including one stretching nearly 1,400 kilometers, diverted river water into the desert for irrigation. By the 1980s, the combined flow into the Aral Sea had slowed to a trickle. In some years, the rivers did not reach the lake at all. The consequences were devastating. By 2007, the Aral Sea had shrunk to roughly 10% of its original size. The fishing industry collapsed completely. The port city that once sat on the shore now sits more than 100 kilometers from the nearest water. Rusting hulks of fishing boats lie scattered across the exposed lakebed, their images among the most powerful symbols of environmental destruction in the modern world. As the sea retreated, its bed was exposed, revealing a poisonous mixture of pesticides, herbicides, and fertilizers that had been washed into the lake from the cotton fields over decades. Windstorms picked up this toxic dust and scattered it across the surrounding region, depositing it on fields, on homes, and in human lungs. Cancer rates rose dramatically. Infant deaths increased. Respiratory diseases and kidney problems became commonplace. Over 100,000 people lost their livelihoods. An entire region was poisoned by the dust of its own dead lake. The Aral Sea is the most extreme example of a pattern playing out across the world. Lakes are shrinking. Rivers are running dry. Underground water sources that took thousands of years to fill are being pumped empty in decades. Lake Chad in the Sahel region of West Africa was once among the largest lakes on the continent. In the early 1960s, it covered roughly 25,000 square kilometers. By the 2020s, it had shrunk to less than a tenth of that area, reduced by a combination of declining rainfall and increased water extraction for the roughly 30 million people who depend on it. The lake's decline has contributed to food shortages, displacement, and conflict across the 4 countries that share its basin. The Dead Sea, the lowest point on the surface of the Earth, is dying by a different mechanism. The Jordan River, which once provided most of its inflow, has been so heavily diverted for drinking water and farming that by the time it reaches the Dead Sea, it is barely a polluted trickle. The sea's level has been dropping by roughly 1 meter per year, and sinkholes have opened along its retreating shore, swallowing roads and buildings. In the American West, the Colorado River no longer reaches the ocean. Its water is entirely consumed by upstream cities, farms, and factories before it can complete its journey. The once lush delta wetlands have largely disappeared. The Rio Grande, which forms part of the border between the United States and Mexico, frequently runs dry in stretches of New Mexico and Texas. Beneath the Great Plains of the United States lies a vast underground reservoir that supports roughly 30% of the nation's irrigated farming. It is being emptied far faster than nature can refill it. In parts of Kansas and Texas, the water level has dropped by more than 45 meters since the 1950s, and some areas may be effectively exhausted within decades. India faces perhaps the most severe underground water crisis on Earth. The country has over 20 million wells, many drilled by individual farmers who pump groundwater with electric pumps subsidized by the government. Each farmer has an incentive to pump as much as possible, but the collective effect is the draining of water sources that took ages to accumulate. Satellite measurements have shown that northern India is losing underground water at a rate of roughly 54 cubic kilometers per year, one of the fastest depletion rates anywhere. A major Indian city experienced a severe crisis when its four main reservoirs ran nearly dry, forcing millions to depend on emergency water trucks. China's Yellow River, once known for its catastrophic floods, ran dry for over 200 days in 1997, the longest dry spell in recorded history, as upstream irrigation and industry consumed its flow before it could reach the sea. The disappearance of lakes and rivers is not just an environmental tragedy. It is a human one. The communities that depended on the Aral Sea, Lake Chad, the Dead Sea, and the rivers of the American West and South Asia are among the most vulnerable people on Earth. Their water was not stolen by a foreign enemy. It was diverted by their own governments, consumed by their own agriculture, and drained by their own growing populations, usually with the best of intentions and usually without enough thought about the long-term consequences. The lesson of the shrinking lakes is simple and unforgiving. Water that is taken from a system does not magically reappear. Rivers that are drained run dry. Lakes that lose their inflow shrink and die. Underground reservoirs that are pumped faster than they refill eventually empty. These are not opinions. They are physical facts as unyielding as the force of gravity. And yet, across the world, they continue to be ignored by governments, farmers, and consumers who assume the water will always be there because it always has been. The rusting boats of that port on the dead shore of the Aral Sea are a monument to that assumption and a warning of what happens when it turns out to be wrong. In the summer of 2018, the city of Cape Town, South Africa, came closer to running out of water than any major city in modern history. The city of roughly 4.5 million people had been gripped by a drought that climate scientists described as a once-in-400-year event. Rainfall had been far below average for 3 consecutive years. The 6 reservoirs that supplied the city had dropped below 20% and were still falling. City officials calculated a date, which they called Day Zero, on which the city water supply would simply be turned off. When that day arrived, residents would queue at 200 emergency distribution points, each person limited to 25 liters per day, roughly enough for drinking, cooking, and basic hygiene. The city fought back with extraordinary urgency. Water pressure was lowered. Leaky pipes were repaired at 4 times the normal rate. Farming was severely restricted. Each person was limited to 50 liters per day, less than a third of typical use in a wealthy country. Public campaigns shamed households that used too much. Hotels asked guests to limit showers to 2 minutes. Day Zero was averted, barely. The rains eventually returned just enough to fill the reservoirs above the danger line. But the crisis laid bare a truth that the rest of the world was forced to acknowledge. The assumption that water will always flow from the tap is not a law of nature. It is a privilege that depends on rain, on infrastructure, on good governance, and on luck. And all 4 can fail at the same time. Cape Town is not alone. A major Indian city experienced its own severe crisis the following year when its 4 main reservoirs ran nearly dry, forcing millions to depend on water trucks. Mexico City, with over 22 million people, has been warned that it faces a similar reckoning as the reservoirs that supply a quarter of its water reach dangerously low levels. The numbers that describe the global water crisis are staggering. Over 2 billion people worldwide lack access to safely managed drinking water. Roughly half the world's population experiences severe water scarcity at least 1 month each year. The World Health Organization estimates that hundreds of children under the age of 5 die every single day from diseases caused by unsafe water and poor sanitation. The crisis is driven by several forces pushing in the same direction. Population growth is the most obvious. The global population has more than tripled since 1950, and the demand for water has grown even faster, fueled by expanding agriculture, industry, and rising standards of living. Farming alone accounts for roughly 70% of all the fresh water used worldwide, and the expansion of irrigated land to feed more people has placed enormous pressure on rivers and underground water. The depletion of underground water may be the least visible but most dangerous part of the crisis. About 70% of the world's major underground water sources show long-term declines, meaning that water is being taken out faster than rain puts it back in. The land above these depleted reservoirs is sinking in many places, a process that now affects more than 6 million square kilometers of the planet's surface. In one Southeast Asian capital, land sinking caused by groundwater pumping, at rates of up to 25 centimeters per year, has made the city so vulnerable to flooding that the national government has committed to moving the entire capital to a different island. Pollution makes the scarcity worse. Even where water exists, it is often too dirty to use safely. An estimated 80% of the world's wastewater is released into the environment without proper treatment. Rivers in heavily industrialized parts of Asia carry toxic loads of metals, chemicals, and farm runoff that make them unsuitable for any use at all. The burden of the crisis falls hardest on women and girls. In many parts of Africa and South Asia, the job of collecting water falls overwhelmingly on female family members, who may spend hours each day walking to distant sources and carrying heavy containers home. The time spent collecting water is time not spent in school, at work, or caring for children. Improving water access in these communities does more than prevent disease. It frees half the population to participate in education and economic life. Inequality runs through every dimension of the crisis. Within countries, the poor always have worse water than the wealthy. Between countries, low-income nations have dramatically worse infrastructure. And between generations, the water that today's populations consume from underground sources that take thousands of years to refill is water that future generations will never have. The solutions are known. Water treatment technology is well understood. Desalination offers independence from rainfall for coastal nations. Efficient irrigation can cut farm water use by 30 to 50%. Rainwater harvesting, wastewater recycling, and smart pricing all work. Israel and Singapore have both demonstrated that water-scarce places can achieve water security through technology and policy. The knowledge exists. It is not the constraint. The constraint is political will, institutional capacity, and money. The United Nations estimates that achieving universal access to safe water and sanitation by 2030 would require roughly $114 billion per year, about 3 times current spending. As of the mid-2020s, no region of the world is on track to meet this target. Progress would need to increase 6-fold to get there. The global water crisis is not a future threat. It is a present reality, experienced daily by billions of people who lack the water they need to survive, to stay healthy, to grow food, and to live with basic dignity. It is a crisis that will define the 21st century as surely as oil defined the 20th. The question is not whether it will get worse. The question is whether humanity will respond with the urgency, the investment, and the cooperation the situation demands, or whether we will continue to treat the most essential substance on Earth as though it will always be there for the taking. In the mountains above the Bolivian capital, at an altitude of roughly 5,000 meters, there was once a glacier called Chacaltaya that was home to the highest ski slope in the world. In the 1940s, the glacier was large enough to support a rope tow, a lodge, and regular competitions. By the early 2000s, it had lost more than 90% of its mass. In 2009, it vanished entirely, 6 years earlier than glaciologists had predicted. The ski lodge still stands, surrounded by bare rock, a monument to a landscape that no longer exists, and a warning of what is coming for glaciers everywhere. Chacaltaya was a small glacier, but its fate is a preview of a much larger crisis. The glaciers of the Andes, the Himalayas, the Alps, the Rockies, and the polar ice sheets are the world's frozen water reserves. They store fresh water in solid form and release it as meltwater during the warm months to feed the rivers that billions of people depend on. As the planet warms, These reserves are melting at speeds that are increasing year by year. The Himalayan glaciers, sometimes called the Third Pole because they hold the largest concentration of ice outside the Arctic and Antarctic, feed the rivers of South and East Asia, including the Indus, the Ganges, the Brahmaputra, the Mekong, and the Yangtze. These rivers supply water to roughly 2 billion people. Climate projections suggest the Himalayan glaciers could lose between 1/3 and 2/3 of their mass by the end of this century, depending on how much warming occurs. In the short term, faster melting actually increases river flow, but this is temporary. Once a glacier passes the point where it loses more ice each year than it gains from snowfall, its contribution to river flow will shrink year after year until it is gone. The communities that have relied on glacial meltwater for thousands of years face a future in which the rivers they depend on gradually run dry. In South America, the glaciers of the tropical Andes provide water to cities, including the Bolivian capital, Bogotá, Quito, and Lima. Lima, a city of roughly 10 million people built in one of the driest deserts on Earth, relies heavily on rivers fed by Andean glacial melt. As the glaciers shrink, the city's water supply grows more precarious with each passing year. Climate change affects water not just through melting glaciers, but through fundamental changes to rainfall patterns. The basic physics are straightforward. A warmer atmosphere holds more moisture, roughly 7% more for each degree of warming. This means that when it does rain, it tends to rain harder. When it does not rain, the drought tends to be more severe because the warmer air draws moisture from the soil more aggressively. The result is a strange paradox. Climate change simultaneously increases the risk of both flooding and drought, sometimes in the same region at different times of year. Monsoon systems, which deliver the bulk of annual rainfall to large parts of South and Southeast Asia, are being disrupted. Research suggests that the Indian monsoon is becoming more unpredictable, with longer dry spells broken by more intense bursts of rain. For farmers who depend on the monsoon to water their crops, this shift is devastating. Too little rain kills the harvest. Too much rain in a single downpour destroys the harvest just as effectively. The narrow band of conditions that supports productive farming is getting narrower. Rising sea levels are the most dramatic water consequence of warming. The rate of rise is accelerating, and even relatively modest projections suggest 1 to 2 meters of rise by the end of this century under high warming scenarios, enough to displace hundreds of millions of people. An estimated 680 million people currently live in low-lying coastal areas, a number expected to exceed 1 billion by 2050. Cities including Miami, Shanghai, Mumbai, and Bangkok face increasing risks of flooding, storm surge, and saltwater contamination of their freshwater supplies. Small island nations in the Pacific face the possibility of complete submersion within this century. Their people may become the world's first communities displaced entirely by water. The oceans themselves are changing in ways that have far-reaching consequences. The ocean absorbs roughly 1/3 of the carbon dioxide released by human activities, and this absorbed gas reacts with seawater to form an acid, gradually lowering the ocean's natural balance. Since the beginning of the Industrial Age, the ocean has become roughly 30% more acidic. This threatens the creatures that build shells and skeletons from minerals in the water, including corals, oysters, and the tiny shelled organisms that form a crucial link in the marine food chain. In the Arctic, ground that has been frozen solid for thousands of years is beginning to thaw. This releases stored carbon as greenhouse gases, creating a feedback loop that accelerates warming. It also disrupts the infrastructure of communities that built on the assumption the ground would stay frozen, causing roads, buildings, and pipelines to buckle and collapse. Indigenous peoples across the Arctic, whose ways of life depend on predictable patterns of ice and water, face the disruption of traditions that have sustained them for generations. Climate change is, at its heart, a water crisis. The floods and droughts, the rising seas and vanishing glaciers, the fiercer storms and shifting monsoons, all of these are water effects. The atmosphere is warming because of the gases we release, but the human experience of that warming is overwhelmingly an experience of water. Too much water in the wrong places. Too little water where it is needed. Water that arrives at the wrong time or fails to arrive at all. The water system that humanity has depended on since the first farmer planted the first seed beside the first river is changing profoundly and rapidly in response to a warming world. Adapting will require investment in water systems on a scale never attempted before, cooperation among nations that share water, and a willingness to reduce the emissions driving the change. Whether humanity is capable of that response remains the defining question of our time. On a summer morning in 2025, on a university campus in Massachusetts, a device no larger than a briefcase sat on a laboratory bench, quietly pulling drinking water out of thin air. The device used a specially designed material to capture water molecules from the atmosphere even in dry conditions where the humidity was as low as 20%. It needed no power source beyond sunlight. It needed no river, no well, no pipe. It simply harvested the moisture that exists in the air everywhere on Earth, even in the driest deserts, and turned it into clean drinking water. This technology, called atmospheric water harvesting, represents one of the most promising frontiers in the story of water. By the mid-2020s, it had attracted hundreds of millions of dollars in investment and inspired dozens of new companies. The technology is still young, producing relatively small amounts at relatively high cost. But the trajectory of improvement resembles the early days of solar energy, when the technology was dismissed as too expensive and too limited before plummeting costs made it the fastest growing source of power in the world. Singapore offers perhaps the most complete picture of what a water-secure future might look like. The city-state, home to about 5.5 million people on a small island with virtually no natural fresh water, has achieved water security through a combination of 4 approaches. It imports some water from a neighboring country. It collects rainwater in 17 reservoirs. It desalinates seawater. And it recycles its own wastewater through a process of advanced cleaning that produces water exceeding the standards set by the World Health Organization. This recycled water, which currently meets about 40% of total demand, is planned to reach 55% by 2060. The idea of recycling wastewater into drinking water faces a psychological barrier that is easy to understand. But the technical reality is that water cleaned by modern methods is purer than most city tap water. One city in Namibia has been doing this since 1968, making it the longest-running example in the world. A facility in California cleans roughly 100 million gallons of treated wastewater every day and returns it to the underground supply from which the county draws its drinking water. Cloud seeding, the practice of sending particles into clouds to encourage rain, has been used since the 1940s. China operates the world's largest program of this kind, employing thousands of people and using various methods to seed clouds over vast areas. The science behind cloud seeding remains debated. Some studies show modest increases in rainfall, while others find no clear effect, but governments facing water shortages continue to invest in it. In the Atacama Desert of Chile, one of the driest places on Earth, a small community installed simple mesh structures in the 1980s that captured water droplets from fog and channeled them into collection tanks. The system produced roughly 15,000 liters of water per day, enough for a small community, using no energy at all. The technology is simple, cheap, and well-suited to remote places far from any power grid. Looking beyond our own planet, the search for water has become one of the central goals of space exploration. A rover exploring a crater on Mars has been studying a site that was once a river delta feeding into a lake billions of years ago. Underground radar has confirmed that the crater once held a vast body of water. The discovery of ancient rivers on Mars, with evidence of water powerful enough to carry boulders, tells us that Mars was once a planet with a water cycle not so different from our own. Understanding what happened to that water, how a world that once had rivers and lakes became the frozen desert it is today, has something to teach us about the fragility of our own planet's water. The possibility of extracting water from ice deposits on the Moon, found in permanently shadowed craters near the poles, is a key part of plans for sustained human presence beyond Earth. Lunar ice could be turned into drinking water, into oxygen for breathing, and into fuel for rockets. The search for water that began with Stone Age farmers digging the first wells has now extended to other worlds. But here on Earth, the most important water technology of the future may not be a machine or a process at all. It may be a policy. Water pricing, which in most countries dramatically undervalues this resource, is increasingly recognized as one of the most powerful tools for conservation. When water is cheap or free, there is little reason to use it carefully. When it is priced to reflect how scarce it truly is, consumption drops and investment in efficiency rises. The future of water will be shaped by the same forces that have shaped its past: geography, climate, technology, politics, and the fundamental human need for a substance without which life is impossible. The technologies are promising. Desalination, recycling, atmospheric harvesting, and fog collection all offer paths to water security that did not exist a generation ago. But technology alone will not be enough. It will require political will, fair investment, and a recognition that water is not merely a product to be bought and sold, but a shared inheritance that must be managed for the benefit of all. And now, as we reach the end of this long journey together, let us take a moment to look back at all the ground we have covered. We began out among the stars, where atoms of hydrogen and oxygen found each other in the dark and created the most consequential molecule in the universe. We followed that water to a young, cooling Earth, where it fell as rain for millions of years and gathered into the first oceans. We saw life stir in those ancient waters. We watched as the first farmers dug the first channels to bring river water to their fields. And we saw how those simple ditches grew into the irrigation systems that built the first civilizations along the Tigris, the Nile, the Indus, and the Yellow River. We walked through the drains and baths of Mohenjo-Daro, 4,000 years old and still astonishing. We bathed in sacred rivers and stood at the edges of cenotes. We heard the flood stories that echo across every culture on Earth, and we met the gods that humans created to explain water's terrifying power. We followed the Mukhanis underground through the Qanats of Persia, and we marveled at the aqueducts that fed 1 million Romans and the water wheels that turned on the Orontes. We crossed the Pacific with sailors who staked their lives on wooden casks. We stood beside Jon Snow as he traced cholera to a pump on Broad Street, and beside Bazalgette as he built the sewers that saved London. We watched John Leal add a carefully measured dose of disinfectant to the water supply of a New Jersey city and change the world. We saw dams rise across every continent, and we watched the Aral Sea vanish into dust. We traced the water cycle from ocean to cloud to river to tap, and we saw how fragile that cycle has become in a warming world. We stood in Cape Town as day zero approached, and in the Owens Valley as its lake dried to nothing. We asked who owns the rain, and we found that nobody and everybody has a claim. And through all of it, the water itself has never changed. Every molecule of water that exists on this planet has been here for billions of years. The water you will drink tomorrow once fell as rain on the first forests. It once filled the cup of a Roman soldier. It once carried a Polynesian canoe across the Pacific. It once ran through the channels of Mohenjo-Daro and fell from the clouds onto a Mesopotamian field. The water is always the same water. It simply moves endlessly through the great cycle that has never stopped turning since the first rains fell on the young Earth. You are at this moment about 60% water. The fluid in your cells carries a saltiness remarkably similar to that of the ancient oceans where life first stirred. as if your body holds within it a memory of where everything began. You are not separate from the story of water. You are part of it. You always have been. And now, as you settle deeper into whatever comfortable place you have found, as the weight of the day slowly lifts and your breathing grows calm, know that the story of water will continue long after this night is over. The rain will fall. The rivers will run. The oceans will rise and recede. And somewhere, right now, a child is cupping water in her hands and drinking, just as her ancestors did 10,000 years ago, just as yours did, just as every human being who has ever lived has done, reaching for the substance that makes everything else possible. The water is still here, all of it. Every drop that has ever existed on this planet is still here, moving through the same ancient cycle. The question is not whether the water will last. The water will outlast us all. The question is whether we will care for it well enough, share it fairly enough, and protect it wisely enough so that it continues to sustain us as it has sustained every generation before. Rest now. Let the story settle gently around you like water settling into a still pool. The journey has been long, and you have traveled well. Good night.